morning here. Good morning. Awesome. So we are back up and running, and we are going to continue our journey talking about renal physiology. And a lot of renal physiology will be based in something that you've learned before, which is quite convenient in my opinion. You guys have probably already started to see that, right? Renal physiology is going to be, it's going to revolve a lot around blood pressure and blood volume. And because one of its major functions, of course, is to filter the blood. So pretty big deal. Plus it helps to regulate blood volume and blood pressure and ion concentration and osmolarity and all these things that act on blood pressure and blood volume, which of course feeds back to the heart. You guys already kind of got an introduction into that yesterday. In addition, we got to remember that the kidneys and the lungs are also really closely related. And the lungs and the heart are also really closely related. We'll be seeing that a lot more as we go into blood pH balance, but I call this the trifecta of body organs. Those three organ systems are so intimately linked that if one of them starts to go out, what you're noticing is that one of those other systems has to compensate. So if the heart's not working quite as well, then the kidneys and the lungs have to compensate to try to fix that problem. Crazy, huh? If the lungs aren't working quite so well, man, now we're not getting proper gas exchange. So we're going to have to get rid of those acids somehow. So the kidneys are going to have to compensate. And we're not getting enough oxygen, so the heart's going to have to try to compensate somehow. Plus the kidneys are going to compensate as well by secreting erythropoietin. So yeah, it definitely, we're going to be getting to all of this in the next couple of lectures. That's all we have left to really look at how the whole entire body works together. And then we'll go into reproductive system, and reproductive system is always the last because it's, it's that organ system that's not necessarily about immediate survival. It's not about keeping you alive right now. It's about passing on your genes and keeping your genes alive. Your cells all want to survive somehow, and therefore they want to pass on their information to offspring. Pretty cool. While we are stopped here, while we are kind of at a really good spot for this, are there any questions over what we went through the last 2 days in terms of the urinary system, the nephron, the basic functions of everything? Are there any immediate questions that need to get answered right now, or you're not going to understand what's coming up next? All right, going once, going twice. Sold. So what we covered yesterday was in essence this idea. We just kind of continued this idea that all filtration occurs in the glomerulus, and we're going to learn about the properties of the glomerulus today that allow that filtration to occur there. We're going to learn about the physiology involved in changing filtration. Once filtrate is pushed into the tubule system, we immediately start to reabsorb. So what are we going to be talking about? The anatomy and the physiology that allows for that reabsorption. We've already started that idea. Most of the reabsorption occurs in the PCT, which means that there's a large number of protein transporters in the PCT for everything that needs to be transported. Whereas in this loop of Henle, the thin portion, what's the only thing that's getting reabsorbed down here in the thin loop of Henle? Water. So we're going to have to talk about the properties of the loop that allow for water reabsorption here. Next is that ascending, the thick ascending limb of the loop of Henle. This is the portion with massive numbers of salt transporters. So we are just moving salt, sodium and chloride and potassium. We're moving all of that back into the bloodstream at this point right here. Versus the DCT, the collecting tubules and the collecting duct, which these were all dependent on hormones. So we're going to end up talking about each one of those hormones and exactly how they're going to be acting on sodium reabsorption and potassium secretion, potentially potassium reabsorption, and water reabsorption. What makes a target cell, everybody? Perfect. And so if these areas are going to be responding to hormones, what must they have? They must have receptors for those hormones. And then we'll talk about the intracellular pathways that allow for their response. Okay, so we got a lot to get through, and it's all going to start with this formula. We know what goes into the system is going to be the biggest number. We got lots of filtrate, thank goodness. 180 liters per day on average. Now, the large majority of that is going to get reabsorbed from the tubule system back into the bloodstream, and a very small, minute amount is going to get secreted by protein transporters back into the tubule system. And whatever is left over at the end of that collecting duct, when it makes it into the minor calyx, that will now be urine. So we call this excretion. So when we go to study the renal physiology, what you should always do first is draw the nephron. So study guide. Oops, that's how you spell guide. There we go. Study guide 1, draw that nephron. Draw a flow chart. Multiple, okay, flow charts of blood flow, energy efficiency, Melissa. We don't want to deal with, oh yeah, I'm just writing that list, but it's all about energy efficiency. Thank you for the reminder on the share screen. But I'm just writing this little list. Study guide, draw nephron, draw flow charts, easy peasy, right? Draw flow charts for both filtration and blood flow. But we are able to do that in the same big flow chart, right? Blood flow. Now we're talking about the renal artery going to the segmental artery, going to the interlobar artery, arcuate artery going up and over those renal pyramids, dividing the medulla from the cortex, and then those cortical radiate arteries that branch out to the afferent arterioles that go to the glomerulus. And then we can actually have a split in our flow chart. One is going to be leading blood back to the renal vein, and the other one is of your filtrate going through the tubule system. Does that make sense? That is a really important set of flow charts for you just to be able to draw, just be able to think about the anatomy of the system. Okay, and it relates to drawing that nephron, because you're going to see the really important portions of the blood flow, afferent arterial and efferent arterial going in. And then the last thing that you want to do is make sure you're thinking that, oh man, whatever comes out at the end of the road, well, that's going to relate back to whatever goes into the system minus whatever we take out of the system plus the little bit that we put back into the system using active transport. And then we were discussing yesterday that filtration is something we're really interested in, because this is the value that is the most homeostatically regulated in terms of determining kidney function. When we look at the kidney function of filtration, we don't call it just filtration. We want to look at how much is filtered over time. So what abbreviation, what acronym do we use for this homeostatic value? What are we actually looking at when we're looking at filtration over time? We're looking at GFR, exactly. So filtration, what we're really caring about here is something called GFR. And the formula that we learned for GFR yesterday, the two major variables that impact the filtration rate of your kidneys, kidney function, pretty big deal, is NFP, net filtration pressure. And we'll write out another formula for this one, but this was one that you learned earlier this semester when we were talking about capillary gas exchange and nutrient exchange. And there's one more piece of the puzzle that we haven't fully discussed yet. I just made you write it down and I said we'd talk about it tomorrow. Well, today is tomorrow. So this is K for coefficient. Yes, I know coefficient starts with a C, but in math, coefficients are just big capital Ks. And it's a filtration coefficient, K subset F. This one will make more sense in just a minute. Let's go ahead, make sure we hash out this NFP one more time because of how important it is. One, for your tests and your homework, but two, in terms of body function, is that if we have a blood vessel, and we're going to say that this is inside of the glomerulus because that's where we're at, right? We're inside the kidney, therefore, and we're talking about filtration, and 100% of filtration occurs between the glomerulus and that Bowman's capsule space, that capsular space. Yes, no? So we're going to go ahead and call this the Bowman's capsule, but it's really the capsular space. And the Bowman's capsule would be, the shell that's around this. So the number one thing that allows for filtration, the number one pressure that allows for filtration is hydrostatic pressure. We know hydrostatic pressure is water pressure that's pushing against walls. Well, there's going to be water pressure both inside of this tube, and there's going to be water pressure outside of this tube, so we better be able to think about each one of these. One of them has pushing power, so is it promoting filtration or is it promoting reabsorption? Filtration, good. And the other one's pushing in the opposite direction. So does it promote filtration or does it promote reabsorption? Why is the value, well, we'll come back to that, but this value inside of the glomerulus is going to be much greater than the value outside of the glomerulus. And there's a lot of properties of the glomerulus and the fenestrations and the pressure gradients that relate to this. But since this is inside of the glomerulus, we want to make sure that we understand that there's a subset for it. We're just going to do a subset G, makes our life a little bit easier. Down here, hydrostatic pressure, we can put BC. I think I did that yesterday. You can just put C. It's whatever makes it so that you know that that is inside that Bowman's capsule. So this would just be capsular space, for instance, right? It's up to you. You could use whatever subset you want. I don't care. Now, the other thing that is determining pressure gradients inside of our blood vessels is the party, right? And let me do this again because not everybody remembered this yesterday. What is the party in your blood? What is the number one source of party? Albumin. All proteins, really. It doesn't just have to do with albumin, but albumins are 60% of your blood protein. So they are the number one blood protein. And they're a little bit smaller than some of the other proteins, so actually they can have a few more issues than some of the other proteins that are in your blood. But yeah, it's that albumin. And so we call this colloid osmotic pressure. Colloid proteins, osmotic because party, and then pressure because that's what we're dealing with here. And so would this have pulling pressure? I shouldn't say pulling pressure. I don't really like that. Does this promote filtration? The colloid osmotic pressure inside of the glomerulus, does it promote filtration or reabsorption. That's right. So it's going to be actually pulling water towards it. Cool. Cool. Now, we're going to be learning about a lot of properties of the glomerulus today that try to prevent, that doing everything they possibly can to prevent proteins from getting from the blood into that capsular space. We don't want the proteins in here, but we want to make sure we think about them. If proteins do get here, is that going to promote filtration or will it promote reabsorption? Well, water wants to be where that party's at, so it's promoting filtration. This is also colloid osmotic pressure, but that's in the capsular space, whereas this colloid osmotic pressure is in the glomerulus. Perfect. So now, what do we know? We know NFP, the net filtration pressure. What's happening net? What is the sum of all of these different things? Well, that's going to be NFP is equal to hydrostatic pressure inside that glomerulus minus, we're going to go with the next biggest value, which is going to be the proteins that are in your blood, colloid osmotic pressure inside that glomerulus. And let's add the things back into the system that are promoting, well, different parts of this, by the way. So the first one's going to be promoting reabsorption. And there is a value for this. This is a relevant issue inside of that capsular space because all of this filtrate is going out into the Bowman's capsule. There's just nothing we could do about that, right? It's building up pressure inside of that Bowman's capsule. Hopefully that pressure is going to create a pressure gradient, which now pushes the filtrate out into the PCT. But before it can go out into the PCT, it's still pushing back against that glomerulus. And the last value, which should be 0, but it would create a party out inside that capsular space, so we add it back to it because it's promoting filtration, is colloid osmotic pressure in that Bowman's capsule. So that's going to relate back to this NFP. Let's talk more about this hydrostatic pressure right here. And let's talk a little bit more about the colloid osmotic pressure inside this glomerulus right here. And we're going to go to our lecture for this. This is a zoom in on that renal corpuscle. Corpuscle is this whole thing here. This also includes the juxtaglomerular apparatus over here. So quick anatomy review. Afferent arteriole, efferent arteriole. Afferent is always bigger than the efferent. What else do you guys see about the afferent arteriole? I'm circling it right now. Because it's an arteriole, what do we know in circles? Good, smooth muscle, right? So we're going to have receptors here. By the way, receptors for both nervous system, portions of the autonomic nervous system. Might as well ask this question now. What subdivision of your autonomic nervous system is the sole portion of the autonomic nervous system that innervates blood vessels? Sympathetic or parasympathetic? Yeah, always sympathetic. There are no muscarinic receptors. There are no muscarinic receptors on the blood vessels of your body, so we're going to be dealing with adrenergic receptors here. Good. This will be really, really important to the system. Very important to the system. We'll be talking more about it. All right, and then these cuboidal cells here, these are the granular cells. They secrete renin. We got these columnar cells over here. These are the macula densa cells. They're going to be communicating back to all this system as well. But let's end up talking a little bit more about what's going on in here. We have the glomerulus, which is surrounded by podocytes. So what are the anatomical features? What is going to be driving the filtration? What allows the filtration to occur? Let's look at the anatomy of this system first. Podocytes have these extensions, these legs, okay? And these legs are covering up most of the fenestrations. These fenestrations are going to be a pretty big deal. They're going to be allowing, think of Swiss cheese. Water is going to be flying through these fenestrations. So that is definitely one of the anatomical features of the glomerulus that really, really promotes filtration. I mean, super promotion going on here because what can go through a hole? Anything small enough, right? So we have these relatively large holes and a whole bunch of stuff is going to be trying to go through them. But we got a problem. We got these foot processes of the podocytes that are covering a bunch of these holes. I don't know if that's a problem. Whatever it is, it exists. We're going to have to think about it. And there's one more thing that most people don't really see here. Yes, they are part of the visceral layer. Great question, Andy. Absolutely, they are the visceral layer. They're not just part of it, they are the visceral layer. But there's one more layer that a lot of people fail to see. You guys notice this is the capillary. This is the fenestration on the capillary. This top layer is the podocyte. These are the legs, in essence, and these are the foot processes that come off. In between each one of these foot processes is a filtration slit. So pretty easy to see those filtration slits. But look, there's one more layer right here. My mouse is going over the top of it. There's one more layer right here. My mouse is going over the top of it. Everybody see that layer? That layer is called a basement membrane. We've seen basement membranes. They lie underneath all epithelial tissue. This basement membrane is very, very unique. So now as we look at a cross section. So here's your blood. You can see your erythrocytes, platelets, leukocytes, large proteins like albumins, or actually large proteins like hormones. Small proteins like albumins shouldn't make it in there. But these large items, they're not going to be able to fit through these fenestrations. And even the really, really small proteins that might be able to make it through fenestrations. What if I keep saying, do we want proteins out here? We want to keep it as small value as we possibly can. We want as very little proteins out here as we possibly can. We want this value to be as close to 0 as possible. So even if we have very small proteins that make it through the fenestrations, we better have some more protective barriers, don't we? Well, the next protective barrier is the basement membrane. And this basement membrane is extremely negatively charged. It's highly electronegative. Why? Why would that matter? You may or may not remember me hearing me say this. When your body starts to break down muscle, can it make it to your pee? Oh yeah, absolutely. Yeah, it's going to start turning the pee like a brown color as all of that myoglobin gets broken down. Rhabdomyosis. Yeah, definitely. Well, and we'll talk about that. Yeah, that's rhabdo. And we won't talk about it much. But there's a property of the kidneys that's interesting. It has the enzymes that can start to break down myoglobin. Myo comes from the muscle. It's basically hemoglobin of the muscle, and it gets released when the muscles start breaking down. And your kidneys can actually metabolize myoglobin, but you don't want that because the metabolic waste of breaking down myoglobin in the kidneys causes kidney damage. So it's going to cause an acute renal failure as that happens. Yeah, big time tangent. So let's get back on board here. So this basement membrane is electronegative, and we're finding out more and more about the electronegativity. There's lots of research going on about this basement membrane and its importance in kidney function. But what is the one thing that I'm going to ask you guys to remember about the negative charge found on this basement membrane? What charge is normally hanging off? What net charge is normally hanging off proteins? Does anybody remember me saying this through the semester? I've said it a number of times, but you guys probably, I've never made you write it down before. Here, I'm going to make you write it down. I got a negative, I got a, the answer is negative. Because if it was a positive charge, Tariq and anybody else that was thinking positive, if the proteins had a big positive charge hanging off of it, wouldn't it be attracted to the basement membrane? Whereas if it has a big negative charge, and this is negatively charged, boom, we got a repel. True story, we got repulsion. Opposites attract. But if they're the same charge, they're going to repel one another. Yes, no, maybe so. You guys on board with this idea? That's a very important part of this system. If small proteins get into the fenestrations, well, good news. We got the basement membrane that's going to do everything it can to repel that. Now, if the hydrostatic pressure is great enough in the system, it can still push small proteins through the fenestrations. It can fight through that electronegative charge, and it's going to get down out here. Well, the only place it can go, because the foot processes cover a whole bunch of stuff, the only location those proteins can go is in between those filtration slits. I got good news for you. These foot processes have receptors on them for small proteins. And as those small proteins get filtered through the filtration slits, they grab onto the excess proteins, the ones that have magically made it through, and then they go through a process of endocytosis and then send it back into the blood. So they're really, really trying to prevent proteins from getting filtered. Every part of this system is, from fenestrations to the electronegative basement membrane to those filtration slits and the podocyte feets. I said feets. Sometimes nothing. Because honestly, like if you exercise, if your BP just shoots up, if you have way too much protein in your diet, that protein is still going to end up in your urine. You're probably going to have polyuria. You're probably going to need to drink a little bit more to try to maintain your blood volume. So definitely finding protein in your pee immediately is not a sign of like, I'm going to die tomorrow. It doesn't even necessarily mean you have kidney failure. It does mean that you pushed your kidneys to the limit. A lot of people that have exercised way too strenuously will have protein in their urine, period, because your blood pressure got so damn high, there was nothing else that your kidneys could do. It is going to cause those fenestrations to open up. And it's basically going to push those proteins through the filtration system. Just imagine coffee. If you were to put too much pressure on a coffee filter, you're still going to get coffee grinds through that coffee filter. You might rip the coffee filter along the way, and that's where you can start having long-term issues. Okay, cool. So now you guys know some of the anatomy that allows this to occur, but let's take this back to our NFP equation. Remember, our NFP is all about hydrostatic pressure in the glomerulus minus the colloidosmotic pressure in that glomerulus. We'll come back to the rest. So whatever pressure system's here is pushing water, glucose, amino acids, ions, urea, some small hormones that can make it through, vitamins B and C, ketones, and a very small amount of proteins. We really don't want them in there, but we're going to potentially have some small amounts of protein. I mean, you'll be okay. All of this hydrostatic pressure is pushing that through the filtration. It's the #1 contributor to filtration. The proteins here are trying to retain water, so it's pulling some water back towards it, slowing down filtration. Yes, no, maybe so. Is everybody on board with this idea? We also have some water out here, right? We got water. And that's going to be pushing back, so that's going to be hydrostatic pressure out here in that capsular space. And we should have very small amounts of protein out here, so the party out here shouldn't be very big. Oh yeah, water just pours through these holes. Yep, for sure. Polar electronegativity does not block water from going anywhere. Yeah, water's just this is purely based on blood pressure. And that's what I want you guys to get to think about next, is we are going to be dealing with the net filtration pressure, which we've already covered in quite a bit of detail, in this filtration coefficient, which I will cover in more detail in just a second. But I want you guys to be thinking about how hydrostatic pressure inside this glomerulus can change. This is the number one. Do your blood proteins change really fast? Are we going to change our blood proteins right now to be able to fix a renal problem? No, right? We're not going to be altering our blood proteins a whole heck of a lot. So this value is pretty darn constant. We need to care. We definitely care about this value in a lot of disease states, right? The colloids inside of our blood can be highly affected by anything from, as I've been mentioning, exercise to dehydration to kidney failure. There's a lot of things that can end up impacting the colloid osmotic pressure. But the number one variable that we're going to change, boom, right now, within 200 milliseconds, is this hydrostatic pressure inside that glomerulus. We can change this. Where does most blood pressure come from? It's coming from heart function. Yeah, exactly, Tariq. Good. And blood vessel function. True story, y'all? Unit 2, all that Unit 2 stuff. So the primary driver of the hydrostatic pressure inside of your blood vessels is related to mean arterial blood pressure. Yes? So if we go, we want to write this down, of course. If we go and start to think about some of the factors that affect hydrostatic pressure here inside the glomerulus, one of those factors has got to be mean arterial blood pressure. It's got to be. We know this is proportional to cardiac output times TPR times that blood volume. So if your blood pressure starts to go up for whatever reason, what's going to happen to that hydrostatic pressure inside that glomerulus immediately? Increase, decrease, no change. Yeah. Does that make sense to everybody? Therefore, what happens to NFP? Increase, decrease, no change. And therefore, if NFP goes up, what happens to GFR? Increase, decrease, no change. And it's this GFR that is homeostatically regulated. We care about GFR. Our bodies care about GFR. So if GFR starts to go up, what's the body going to try to do to GFR? Increase it more or decrease? Or no change. No. You got it. It's going to bring it back down again. And we got to figure out how it can go about doing this. All right, let's go in. Okay. Here's just some values, the hydrostatic pressure. Oh, by the way, we forgot about one more important part. Even though we've discussed it, but I want to make sure that we understand it. Hydrostatic pressure inside the glomerulus is way higher than the hydrostatic pressure in most capillary beds. 60 millimeters of mercury is really high relative to capillary beds around the rest of the body. Capillary beds around the rest of the body, you got a hydrostatic pressure of about 35. And yet here, it's 60. So why is the hydrostatic pressure so much higher? Good, Tariq. What do you mean by that? Because of the amount of blood going through. What do you mean? Are you just saying because there is 20% of the blood? That's one thing. Yeah. That's one thing. Let me give you guys a hint. I'm not doing a verbal hint, I'm doing a visual hint. You remember me talking about how the afferent arteriole is bigger than the efferent arteriole? Yes, no, maybe so? More blood enters than can leave. More blood enters than can leave. And what's that going to do to the pressure inside that system? It's going to bring it up. So the hydrostatic pressure inside this glomerulus is much higher than it would be in most other capillaries of the body because we have an anatomical feature that allows it. And that is going to allow for all of that filtration to be driven through the fenestrations and the basement membranes and the, filtration slits. Pretty cool. Colloid osmotic pressure is not going to change because proteins should not get filtered out. So the colloid osmotic pressure going in should be the same as the colloid osmotic pressure going out. Okay, you guys get all that stuff. So I want you guys to be thinking about this idea of mean arterial blood pressure and as it relates to blood entering this system. This blood entering the glomerulus is coming from your blood stream, your normal bloodstream, driven by blood pressure. So if blood pressure, mean arterial blood pressure goes up, that's going to cause more blood to enter this system. Yes, no, maybe so? And that's what we were discussing right here. If we end up having an increase in our blood pressure, the hydrostatic pressure inside that glomerulus is going to go up because more blood is entering through the afferent arteriole. Therefore, GFR is going to go up and more filtrate is going to be entering these tubule systems. And what did we say the body's going to try to do to GFR? Increase, decrease, no change. If it starts to go up too high, bring it back down. We want to bring it back down. So, homeostasis. So, since the number one factor that determines GFR is the hydrostatic pressure in the glomerulus, and that's driven by blood pressure going through the afferent arteriole, what is the fastest thing the body can do to try to bring that GFR back down again? Go ahead. Decrease BP. Do we want to decrease the overall body's blood pressure? So for instance, let me take a step back. Let me just take one step back. Okay, blood pressure changes just because we stand up and sit down. Like, blood pressure is not always just an emergency response change. Do you remember me saying that earlier this semester? You just move. If you move, your body is constantly fluctuating, sympathetic and parasympathetic, small, tiny differences. Your blood pressure can change by 1 millimeter of mercury, 2 millimeters of mercury. It doesn't have to be huge, drastic changes in blood pressure. But small changes in your mean arterial blood pressure will create changes in your GFR. Small changes, but still a change. And we don't want to try, if we're up walking around, just because the GFR goes up doesn't mean we want to drop the overall mean arterial blood pressure, because then not enough blood's getting to your brain as you're trying to walk from point A to point B. Does that make sense? But just because we're walking from point A to point B doesn't mean we want to have an increase in GFR. So we're going to bring that GFR back down. We need to regulate just what's happening at the kidneys. We don't want to impact the rest of the body yet, unless there's a chronic effect. So how can I bring down GFR without impacting mean arterial blood pressure? Just by looking at this figure, I'm trying to get you guys to think, to logic. Yeah, good. Good. Everybody read Becca's response and Sabrina's response. And maybe start using that in your own idea, your own thought process, and try to write something down in chat for me. I mean, there's 18 of y'all here, so I'd love to have more responses. Maybe tell me what's going on, what's happening. Yeah, Andy, good. Yep, smooth muscle, sympathetic nervous system. Sometimes, Becca, that will be a reflex loop. There's going to be both intrinsic and extrinsic properties affecting this. But yeah, definitely want to think about those smooth muscles. Good. Everybody take a deep breath. Since the number one factor driving GFR is hydrostatic pressure in that glomerulus, and the hydrostatic pressure in the glomerulus is dependent on blood flow into that glomerulus, let's just change blood flow into that glomerulus. This is going to impact just the nephron function and not change the rest of your body's blood pressure. When you need that blood pressure high, even if you're running from Mr. Axeman, it's not like we want to pee more. So we don't want more GFR when we're running from Mr. Axeman. Does that make sense? So the kidneys are going to have to figure out a way to regulate themselves. And the easiest and fastest way to regulate kidney function is this afferent arteriole. There's circular bands of smooth muscle around it. So if we were to vasoconstrict this afferent arteriole, what just happened to the resistance through the tube? Increase, decrease, no change. And if we increase the resistance, what happens to blood flow through this tube? Increase, decrease, no change. Less blood in, what's going to happen to the hydrostatic pressure inside this glomerulus? Increase, decrease, no change. And as we decrease that hydrostatic pressure in the glomerulus, what's going to start happening to NFP and GFR? Boom. Increase, decrease, no change. And we bring it back to normal levels, right? So if we have normal flow, if we have blood flowing to all the organs of the body and renal blood flow in, well, all of a sudden, we have an increase in blood flow to the other organs of the body. There's an increase in MAP for whatever reason. We have an increase in GFR. Well, man, if we vasoconstrict the afferent arteriole, less blood can now flow in, decreasing that hydrostatic pressure, decreasing that GFR. There are receptors on the afferent arteriole, but there's also going to be intrinsic properties. I keep mentioning those, and I'll keep mentioning those. Yeah, you don't need to have big body responses. We can have nice little local responses if that's all that's needed. What if I wanted to increase GFR? What could I do to increase GFR? Sure, we could relax the afferent a little bit. The afferent's already pretty big. The afferent's already pretty big. We can't relax it too much more, although we can. Don't get me wrong, there is some vasodilation that can occur here. But what if we want a more drastic change in GFR? Ah, good. We still got another arteriole on the other side, y'all. We still have another arteriole, and what do arterioles have around them? Circular bands of smooth muscle. So why not vasoconstrict that efferent arteriole? If we vasoconstrict the efferent, what's going to happen to resistance in this tube? Increase. What happens to blood flow? Out. Decrease. And if less blood flows out, what's going to happen to the hydrostatic pressure inside this system? And now we got an increase in GFR. Does that make sense? Cool, cool. Awesome, love it, guys. This is exactly what we're trying to get to. How can the body go about changing GFR? It's always going to be hinted up, I shouldn't say always. The large majority of the time, it's going to be affecting that afferent and efferent arteriole, okay? Hormones, autonomic neurons, this is extrinsic effects. We're going to have massive changes in blood flowing in and blood flowing out. Yes, no, maybe so? Awesome. Cool. Now, one more step back, because let's go back actually to this image, because there is one other thing going on here, which is that filtration coefficient. So I'm going to explain this filtration coefficient now. Do you guys remember me talking about these weird little subset of cells right here? Maybe, maybe not. These ones are called mesengial cells. MESENGIAL, mesengial cells. And these mesengial cells have the ability to contract and relax. And the glomerulus kind of builds itself around these mesengial cells. You know, the mesengial cells extend in a little ways, and these guys can actually contract and relax a little bit. Now, what does this mean? The analogy that I like to use is, think of a fist. Okay, and you're just going to take your hand and you're going to loosen that fist, and you're going to create that fist. You're going to loosen that fist. And as you loosen that fist, what happens to the space between the fingers? It's increasing. Which one of these, a loosened fist or a tight fist, which one has a greater surface area? Loose. You got it. And therefore, which of these is going to allow more filtration? Loose or tight? Does that make sense to everybody? I got a lot of people here that aren't answering, so I hope everybody's following along. This filtration coefficient is all about, well, not all about, one of the things that controls this filtration coefficient is surface area. And we can change the surface area of the glomeruli because the mesengial cells are able to take and tighten the glomerulus, cause them to contract up in probably a pretty creepy way if we ever saw it live, and relax. So when we go to look at this filtration coefficient, we can break it apart, where the KF is going to be equal to something, or proportional to something. The filtration coefficient is all about surface area. As surface area increases, we can filter more. So the filtration coefficient will increase with it. As we alter the surface area, we'll alter filtration. The next thing has to do with a value we've talked about also with the rate of diffusion and stuff like that, which is membrane permeability. MP stands for membrane permeability. And if we go back to this picture, membrane permeability, what we're talking about is the permeability of these different things, whether it's water, glucose, amino acids, ions, urea, whatever, through fenestrations, basement membrane, and filtration slits. What do we know about fenestrations? What can go through a fenestration? Anything, help me help you, anything small enough. It doesn't just have to be little, Andy, I like what you're doing, but it's just got to be small enough to get through that hole. So what if we were to change the size of this hole? What if we were to make that hole a little bit bigger? What's going to happen to the speed of material going through it? Increase, decrease, no change. And we make that hole a little bit smaller. So now what I want you guys to do is imagine a glove on my hand as I'm making this fist. So as I put a glove on my hand and then I stretch that glove out. As I really increase my surface area of my hand, what's going to happen if you take that, a balloon, put a small hole in it, and then stretch that balloon out? What's going to happen to the size of that hole? Increase, decrease, thin out for sure, but what's going to happen to the size of the hole? Increase, decrease, no change. Is everybody on board with that? Therefore, what's going to happen to the movement of material through that hole? Well, it's bigger, more stuff, faster, sweet, awesome. So this is the link I want you guys to make. is that membrane permeability and surface area in normal physiology almost always change at the same time. Because as surface area increases, the membrane permeability will increase with it. There are a lot more properties that go into membrane permeability, like the electronegativity of the basement membrane, but I don't want you guys to have to deal with all that stuff. So work with me. As surface area goes up, we stretch out those fenestrations ever so slightly, and more material can pass through it. Whereas now, as we tighten our fist down, we're taking that balloon with holes in it, that rubber glove with holes in it, and we're relaxing that, which now allows for that hole to return to that nice small size. Does that make sense? So these two things tend to move together. Surface area goes up, membrane permeability will go up. Surface area goes down, membrane permeability will go down. They tend not to move in opposite directions. Yes, no, maybe so? And so that's the other thing that's going to be altering GFR. If we alter that filtration coefficient, if we increase the surface area of the glomerulus, it will impact that membrane permeability, and it increases the area that filtration can occur across, so that will also alter GFR. Hormones in the autonomic nervous system can do both of these things: alter arterial size, and change the filtration coefficient. We're going to see how in just a minute. Now, there are also a couple of intrinsic controls. The first one's called myogenic, and the next one is called, thank God it's Friday, TGF, tubuloglomerular feedback. I always just try to come up with a few things for you to remember it, right? TGF, tubuloglomerular feedback. We're talking about this, and it'll be one of the last things we talk about. This is the only location that we talk about myogenic responses. Myo, muscle. Genic, local. So we have an intrinsic ability of smooth muscles to be able to respond to their changes. We've seen this before. They have a bunch of cytokines and stuff that they can secrete that change their diameter. I don't want you guys to have to think about all those again, but we're talking about different prostaglandins and prostacyclins and thromboxane A2 and nitric oxide and all that sort of stuff. Let's not worry too much about that. Let's just try to imagine if we end up having too much pressure against the walls of the afferent arteriole. What can the afferent arteriole do? It can immediately try to vasoconstrict. It might increase the pressure in that system a little bit more, but what this thing knows is that if the pressure is too high, that means too much blood is going into the system. So as a response, as a myogenic response, it can immediately vasoconstrict ever so slightly to try to decrease the blood flow into that glomerulus. Does that make sense in terms of an immediate intrinsic response called myogenic? Lovely, lovely. Right, this is just a form of autoregulation. It's trying to take care of itself. It can only fix small problems, though. It's not going to be able to fix large problems. But this is exactly what we need if we're like just, standing up from a chair. We don't need big changes. We need really small changes. Next system that comes into play is going to be our extrinsic response. Extrinsic, meaning from outside the system, hormones and autonomic neurons. The next slide kind of goes into this in even more detail, but I want you guys to be thinking about it beforehand because, sorry, that's my style. I don't want to just read a damn slide to you guys. I want to make sure you guys are thinking about it and learning from it. So we can actually write our lists: intrinsic versus extrinsic. Intrinsic, so far we have myogenic responses. Sweet. Myogenic, local changes in oxygen levels and CO2 levels and nitric oxide levels, all of that stuff, all that metabolic processes, right? And then just changes in pressure. So myogenic, all local. Extrinsic controls, we know through the rest of the semester, we've seen this over and over and over again. This is related to autonomic nervous system and hormones, endocrine system. Autonomic nervous system. This is a capillary with afferent and efferent arterioles. We've already covered this today, but redundancy is the key to learning. What autonomic nervous system is going to be coming into play here? What subdivision? Sympathetic. Good. So we know we got the sympathetic nervous system here. Therefore, what neurotransmitters? Because we're talking about normal everyday function. What neurotransmitters are going to be acting on the kidneys? What neurotransmitter? Yeah, now we're talking about norepinephrine, right? So as a neurotransmitter goes, we're talking about norepinephrine, not epinephrine. Epinephrine is a neurohormone. Everybody feel somewhat comfortable with this idea? I hope so, because we've talked about it so much. Now, the adrenergic system's a little wonky down here. I'm not going to talk too much about beta-1 adrenergic receptors because earlier this semester I taught you guys that beta-1 are basically just found on the heart. Well, beta-1, we do find beta-1 adrenergic receptors in other portions of the body, including the brain and in your kidneys. But let's just let's ignore that for now. The body is so complex that you can't possibly learn everything. The deal with beta-1, knowing a little bit that there is a 1 there, what do we know about 1? Adrenergic receptors that end in 1. Are they typically excitatory or inhibitory? Which is cool, right? We need to be able to excite some of these muscles down here because that's going to cause vasoconstriction. What if we want to cause vasodilation? What type of adrenergic receptor is going to really help with that? Beta-2. Good. In addition, all arterioles of the body also have, what did you guys learn about in unit, what was it, unit 2? What adrenergic receptor is going to be found on all arterioles of the body? Alpha-1. Sorry, I didn't mean to throw you guys for a loop. But there's, of course, going to be some alpha-1s down here as well. So the two that I'm going to have you guys focus on the most are going to be alpha-1 and beta-2. Fair enough. Same thing that I did earlier this semester, trying to make sure that redundancy is in there so that you guys are, you know, focusing on the important stuff. That is that if we activate those alpha-1 adrenergic receptors, vasoconstriction of the arterioles, and if we activate beta-2 adrenergic receptors, that's with epinephrine, then we're going to start to impact the system another way. Yes, no, maybe so? We're going to vasodilate. True story? Okay, cool. So norepinephrine acting on adrenergic receptors. Primary adrenergic receptors we're going to be dealing with are alpha-1 and beta-2. Cool. So make sure you guys have these, you know, basics. These are literally basics at this point. Hormones. We got to try to remember what we're dealing with here. Hormones are not immediate. Hormones are going to be more of a long-term response. True story? Hormones don't typically act super immediate. They have these much longer drawn out effects over hours, if not days. And so I'm just taking you guys through the logical steps for what hormones we're going to be dealing with here. The hormones that affect the kidneys are going to be related to hydrostatic pressure inside that glomerulus. And we know the hydrostatic pressure inside the glomerulus is related to mean arterial blood pressure. So what hormone was released when mean arterial blood pressure dropped? Probably the most important hormone for you guys to learn this semester. Yeah. Y'all, what hormone? It's actually technically not even a hormone, but we're not going to get into the whole, it's an enzyme, not a hormone thing. It's an enzyme, not a hormone, but we call it a hormone anyways. Yeah, what is going to be secreted when blood pressure drops? Renin. So if we're just thinking about the fact that we're dealing with net filtration pressure and GFR, and net filtration and GFR is primarily related to the hydrostatic pressure, and hydrostatic pressure is primarily related to MAP, it gives us a tie with something we've learned before. We know MAP is controlled when there's a decrease in MAP. That causes secretion of renin, which does more stuff, right? Renin, angiotensinogen, ANG2, ACE, ANG1, ACE to ANG2. Everybody, yes, no? So we know renin is always going to end up resulting in the release of ANG2, and then what does ANG2 cause the release of? What two hormones will always be released when ANG2 levels are high? Good, great job. If you're not writing it down, hopefully you're able to say at least one of those in your head, ADH and aldosterone, right? These two are going to be activated by the release of ANG2. ANG2 in and of itself has a lot more effects. It's a very powerful hormone. And it's going to be causing the release of two other very powerful hormones. What about when there was an increase in mean arterial blood pressure? What hormone is released here? Good, good, great job. Hard sometimes. Hard to go back into that memory bank and pull this stuff out. So ANP, atrial natriuretic peptide. Did that ring a bell for all y'all that were sitting there digging in your brain going, I know I learned a hormone. I know it's in there somewhere. I know it. I know it. I do. That's how I feel about like basic words nowadays. I know physiology too dang well, and I just can't even come up with like just a basic word for something anymore. And I'm digging. I'm like, it's in there somewhere. An AMP, atrial natriuretic peptide, of course, this is released by the heart. It causes us to pee more sodium. It also has a lot of other effects. One of its major effects that you learned about earlier this semester, but probably forgot about, is to inhibit renin. It's a very powerful inhibitor of renin. It's also going to directly inhibit ADH release, and it's going to directly inhibit aldosterone release. When blood pressure goes up, we definitely don't want any of these, ANG2, ADH, aldosterone, we do not want those in the system at all. So if I can use this same knowledge, this same foundation to try to understand the hormones that are going to control GFR, and I know GFR is primarily related to hydrostatic pressure inside that glomerulus and this filtration coefficient, well, I know about this. And I know that this is related to mean arterial blood pressure, and that we've already learned that renin and AMP are two primary controls of mean arterial blood pressure. Maybe you were able to make the link back here. If not, I'm just trying to help you guys come up with ways to study. That's all. So the primary hormones we're dealing with here are going to be renin, but of course renin is associated with Ang2. And then the other is AMP. Now I'm going to go one more step. Again, this is something that was taught earlier this semester, but probably just sitting back there tickling your brain, is that there is another way that renin can be released. It doesn't just have to be blood pressure dropping. Does anybody else remember what else can activate renin secretion besides blood pressure changes? It's a little bit counterintuitive. But sometimes we want blood pressure to go up, even when blood pressure hasn't dropped already. What about if you're running for Mr. Axeman? What do you want to have happen to your blood pressure if you're running for Mr. Axeman? If you're playing in a soccer game, what do you want? What do you want? Yeah. So the sympathetic nervous system is actually a direct activator of renin. As we fire the sympathetic nervous system, it's going to cause renin secretion. It's going to bypass this decrease in blood pressure issue, and it's going to go straight in and say, we need to bring blood pressure up because we need more blood flowing to the muscle and to our heart and to our brain. Okay? So this sympathetic nervous system over here can actually activate that renin. All right, cool. I think we're ready to just roll. This next part's the hardest part, so that's why I'm making sure that you guys understood the logic behind the foundational knowledge that you already had. If you're running for Mr. Axeman, do you want to pee more or do you want to pee less? Less. You're too busy running from Mr. Axeman. Yeah. You always see those videos of, or whatever. I'm so scared you peed yourself thing. But that's not it's not a factor of making more urine. It's just your bladder doing a quick contraction because of the fright. It's not your kidneys actually having better function when you're running for Mr. Axeman. So if we're running for Mr. Axeman, we don't want to waste our energy making more pee. So what's going to happen to GFR? Let's look down at the bottom of this flow chart. What's going to happen to GFR? Increase, decrease, no change. If we're running from Mr. Axeman. All right, cool. We got a beginning of a flow chart. We got an end of the flow chart. Let's fill in everything in between. So what's going to happen when we're running from Mr. Axeman? We got, first off, sympathetic stimulation. Sympathetic nervous system, alpha 1. That alpha 1 is going to end up causing a change in blood flow. What it's going to do is it's just going to shut down this system, period. It's going to vasoconstrict. As an emergency response, it's going to vasoconstrict everything, both the afferent arteriole and the efferent arteriole. Here's the deal. A lot of students go, well, if the efferent arteriole gets vasoconstricted, that means blood pressure just went up in here because we're, creating a decrease in blood flow out, right, Dr. H? Don't forget, blood flow in must happen before blood flow out. Yes, Heather. Yeah, exactly. We are diverting all this blood, this 20% of your blood volume that's going to your kidneys. We're trying to divert it away from the kidneys. Exactly. But does that make sense? If we vasoconstrict the afferent arteriole and the efferent arteriole, it will result in a decrease in blood flow into that glomerulus. Even though less blood can flow out, it doesn't matter if we pinched off this afferent. And if less blood flows in, we drop that hydrostatic pressure inside that system, and that's going to decrease that GFR. Lovely. Cool. So what else is going on? The sympathetic nervous system is a direct stimulator of renin. And it's that juxtaglomerular apparatus, it's those granular cells that secrete renin. So the sympathetic nervous system is going to talk to those granular cells. Renin is secreted. It's an enzyme that now converts angiotensinogen into Ang1. ACE is already in your bloodstream. It's going to convert Ang1 into Ang2. So now we have more Ang2 in the system. And angiotensin 2 is going to cause contraction of those mesangial cells. The mesangial cells contract, causing that fist to tighten down. So what just happened to the surface area? Increase, decrease, no change. What just happened to the membrane permeability of that system? Increase, decrease, no change. Therefore, what just happened to the filtration coefficient? Increase, decrease, no change. So at this point, we've decreased both GFR and the filtration coefficient. Sorry, we decreased both NFP and the filtration coefficient, and that's exactly what our formula is. GFR is proportional to NFP times filtration coefficient. Filtration coefficient just plummeted. NFP just plummeted. GFR just got shut off. Make sense? Awesome. Alternatively, if we need to increase our GFR, say for instance, blood volume is too high, blood pressure is too high, do you want to pee more or do you want to pee less? If we have too much blood volume and that's causing your blood pressure to shoot through the roof, yeah, we got to get rid of that stuff. Go drink a gallon of water. You're going to pee. You better pee or I might kill you. Right? So as that happens, the atria is going to stretch. It's going to release AMP into the system. AMP is a direct inhibitor of renin. So the right side of our chart is going to be inhibited. There's no Ang2 in the system. And if there's no Ang2 in the system, then Ang2 can't cause mesangial cells to contract. Therefore, they relax. And what's going to happen to the surface area of the glomerulus? Increase, decrease, no change. What's going to happen to the membrane permeability of that glomerulus? Increase, decrease, no change. Therefore, what happens to GFR? Increase, decrease, no change. And at the same time, if we have AMP, AMP is a potent vasodilator. So AMP receptors around the afferent and efferent arterioles, well, primarily the afferent arteriole is going to be affected. It's going to cause maximum relaxation of that afferent arteriole. Blood flow in to the glomerulus is going to increase. Hydrostatic pressure inside the system increases. NFP increases. Therefore, GFR increases. So now we got both NFP and the filtration coefficient going up, and GFR goes up with it. Does that make sense? Awesome. You guys rock. You guys just learned like most of the extrinsic controls of kidney function in like whatever, 5-10 minutes basically. Why? Because it's based off of previous knowledge. Are there any questions about that? Maybe when you guys have some. AMP has beta-2 receptors. No, AMP has AMP receptors, Ashley. What makes a target cell a target cell? Receptors for that. Receptors for that, right? So AMP, it's not going to act on those beta-2 receptors. Beta-2 receptors are going to act through other, we're not even going to be really talking about those beta-2 receptors. How about that? You're not going to be tested on them. You got plenty of stuff to go through. Can drugs interfere with this process? You better believe it. Will most drugs interfere with this process? You better believe it. Yeah, definitely. Yeah, there's always side effects to the drugs that you're taking. Pharmaceutical, recreational, doesn't really matter. Okay, next, let's talk about the last one on the list, the TGF, the tubuloglomerular feedback loop. Now, TGF comes into play as an intrinsic control. It's an intrinsic control. It's an additional level of protection. Okay, so TGF, tubuloglomerular feedback. It's not that complicated of a system. There's one little trick to it that you guys are going to have to learn about. But this all has to do with the JGA. So this is all going to filter back. That's probably the wrong terminology to use here, but it's going to lead back to the JGA. JGA, juxtaglomerular apparatus. So if you're talking about the juxtaglomerular apparatus, we should be talking about the macula densa cells and the granular cells. Yes, no, maybe so? Okay. All right, so let's get back to the lecture here. What you'll see is that we got to remind ourselves of that JGA. We got to remind ourselves that every single, ascending limb of the loop of Henle, DCT, is going to go back from whence it came. It's going to come back into contact with the glomerulus that the tubular system came from. And it's going to typically split right between the afferent and the efferent arterial. And at this point, we find the macula densa cells. And then surrounding the afferent arterial, we find those granular cells. What do granular cells secrete? Namurenin. Gotta believe it. It's that renin. Now, the macula densa cells are tricky ones because I mentioned this a few days ago, but they're actually sensing salt level. They are detecting the amount of salts in the system. The more salts that are in the system, the more cytokines these things secrete. Cytokines are local paracrine signals. Paracrine means they do not go into the blood. Para, surrounding. So they're secreted from these macula densa cells, and they communicate with surrounding cells. Well, look what cells are surrounding the macula densa cells. The cells of the afferent arteriole. Yes, no, maybe so? You do not need to know what these paracrine signals are. There's all sorts of paracrine signals. One of them you might recognize. It's called COX-2, COX, C-O-X. Anybody ever heard of that? Anybody ever heard of a COX inhibitor? You probably have. It's called aspirin. You know of a coccyx bone, yeah. But COX inhibitors, COX, that's actually what aspirin is. All NSAIDs, non-steroidal anti-inflammatories, are COX inhibitors. Well, not all, but many of them are COX inhibitors. They work through the COX pathway. So these sorts of pathways can be affected, again, like what Heather was saying. Will drugs affect the system? Yeah, simple drugs like aspirin. Aspirin alone can end up impacting your blood. And anyways, we don't need to get too much into that. There's all sorts of crazy side effects in the world around us. So here we go. Paracrine signals released by that macula densa cell. So let's go to this figure here. Let's not worry about GFR increasing just yet. Well, why not? Let's actually go straight there. If GFR increases, what's going to happen to the amount of fluid entering the tubule system? Increase, decrease, no change. Therefore, what's going to happen to the speed? Because everything's dependent on gradients. What's going to happen to the speed of fluid moving through these tubes? Increase, decrease, no change. Good, increase. And if the speed through these tubes increases, what's going to happen to the available time for reabsorption? Increase, decrease, no change. Yes, good job. So now, since the fluid's moving faster, less can be reabsorbed. So what's going to happen to the amount of salts in the system? Increase, decrease, no change. If less salt is getting reabsorbed. Increase. Let's rethink that, okay? The filtrate's flowing so fast that it's sliding right by these transporters. The transporters that are in these cell membranes, they need time for their function. And if we hypersaturate the system with filtrate, then too much fluid and too many salts are going by these transporters. Transporters just can't possibly keep up. Does that make sense? So the amount of salt staying in the tubes is going to increase. The amount of salt staying inside the tubes is going to increase. As flow increases, the amount of salts inside that system increases. And those salts pass those macula densa cells. And these macula densa cells are these little osmoreceptors. No worries, Heather. I figured as much. So now we got these osmoreceptors, these salt sensors, and they say too much salt. Therefore, they know GFR is too high. What are they going to try to do to GFR? If it's too high, if there's too many salts? Increase, decrease, no change. Decrease. And what's the fastest way that they can do that? Look at what's living right here, the afferent arteriole. Ooh, MSG, so yummy. Keep going though. What do we want to do to bring GFR down? Do we want to vasodilate or vasoconstrict this afferent arteriole? Boom. It's that simple. It's that simple. As GFR increases, flow through the tubes is going to increase, and that's going to increase the amount of salt that stays in the tubes because less salt can be reabsorbed. That's going to increase the flow of the filtrate past those macula densa cells, and the macula densa cells sense all that salt. They're going to secrete a paracrine signal. That paracrine signal goes and talks to the afferent arteriole, and it's going to cause vasoconstriction. And as the vasoconstriction occurs, it increases resistance, decreases blood flow, and as that blood flow decreases, less blood goes into the glomerulus, dropping that hydrostatic pressure, dropping NFP, and dropping GFR back down again. Salt's so bad for kids. Kids are so resilient. Just everything in moderation. That's all I got to say. All right. That's, yeah, babies for sure. I mean, yeah. I mean, mother's milk has plenty of salts in it. I mean, everybody needs salts. There's so much hate on salts. It's not a problem with salts. It's a problem with the overall damn diet. Don't get me started on dietitians. Dietitians could all, they could use a lot of lessons in physiology, in my opinion. Some of them are great because they actually understand physiology, but a lot of them are just like fat, 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 fat. Fat's not bad. Cholesterol's not bad. It's about the ratios of everything that we're intaking. That's bad. So don't give your kid a salt lick. Don't give them a popsicle after everything that they do. That's my opinion on it, based in physiology. Yeah, just give them chocolate. Anywho, does everybody kind of see this? GFR goes up, TGF is going to kick in. TGF is only when GFR increases. That's it. AMP takes a little bit of time to work, so we need to make sure we have like an emergency brake for the short term. Because the myogenic response isn't strong enough to be able to handle very large changes in GFR. Okay, it's 10:24. One more step that I want you guys to think about. This will be the first time you guys have had to think about this. But let's look at the opposite. what if GFR decreases? What's going to happen to the amount of filtrate entering this system? Increase, decrease, no change. Therefore, what's going to happen to the speed or the rate that filtrate is moving through the tubes? Increase, decrease, no change. And what's going to happen to the time that this filtrate is moving past transporters? Increase, decrease, no change. What's happening to the time? It's moving more slowly, so there's more time. So what's going to happen to the amount of salts and everything in the system? What's going to happen? Exactly. So now the transporters have more time to be moving everything back into the bloodstream. You're all right, Tariq. No worries, buddy. I'm not on my A game like ever. So now we're moving a more dilute solution through the system. And when it goes by the macula densa cells, the macula densa cells say, cool, right? Not dealing with salt here, but what's going to happen to the paracrine signals being sent out? Increase, decrease, no change. So as we start to lose those paracrine signals, that's when the granular cells start freaking out because they're like, wait a minute, well, but GFR must be too low. So what hormone are those granular cells going to start to secrete when that GFR decreases and less salt is measured by the macula densa cells? So this is how renin is actually secreted. Okay, it's not magic. It's not like blood pressure drops, therefore renin is secreted. We got to have a bunch of signal cascades for this to even occur in the first place. Does that make sense? Just always want to make sure you guys understand that nothing in the body is magic. I love magic. Why not, right? But unfortunately, that's not how the human body works. Let's take a break. It's 10:27, so let's go ahead and take a break to 10:45. Yeah. That sounds like a dangerous thing. Cool. Let's go ahead and make it 10:50. Everybody be back at 10:50. All right. So here's where we're at. We have a summary of basically what you need to study for this particular unit. You need to be able to draw a nephron, label it, understand each part of it, draw flow charts, blood flow, nephron. You need to be able to look at this equation where whatever comes out of the system is going to be related to what goes in minus what gets reabsorbed plus whatever we add back to it. The first of these variables, when we go, how does the body alter that excretion? How is it changing that urine volume? Because we got to remember excretion is related to urine volume. How can we change that urine volume? Well, the primary variable is going to be this GFR. This is renal function. When you guys are working in the field, if you guys are working in the medical field in the future, which I hope every single one of you does, and you come across a patient that's got any sort of renal deficiency, renal failure, you're going to be exposed to monitoring, measuring their GFR. It's just part of the deal. GFR is just like cardiac output. It is a measurement of that patient's kidney function. If GFR starts to drop, we know that patient is going into some form of kidney failure or potential kidney failure. It doesn't mean that they have to be in kidney failure right now, but it definitely is going to play a role in that. Okay, normal GFR, in essence, is going to be related to how many liters per day are being filtered. And we already kind of have an idea. We got about 180 liters per day that are being filtered. True story? 180 liters per day that are being filtered. Now, that doesn't mean that it's going to be 180 liters every single day for every single person. If you're at 120 liters per day, then you're okay. You're starting to get into where kidney function might be a little bit on the low end, but not low. You're still healthy. You're still happy. 120 liters per day. Now it starts getting below that. Now we're going to have to start looking into renal failure. So we really care about this value, GFR. I hope you guys are understanding. I will test you on GFR in a number of different ways. Cool news is that GFR, when we're looking at body function, how can we regulate GFR? We're looking at two primary things, NFP and the filtration coefficient. These are regulated by both intrinsic and extrinsic effects. Everybody feel pretty comfortable with that based on what we did earlier today? Awesome. Awesome. We end up talking a lot more about these hormones. I'm going to talk a little bit more about like ADH and aldosterone right now, but you're going to get tested on renin, you're going to get tested on Ang2, and you're going to get tested on AMP. It plays such a vital role in body function, from mean arterial blood pressure to kidney function. So just make sure you keep that in mind as the study guide goes. Cool. Now, we're not done yet with this equation, because all we've talked about so far is that filtration. What is left? Reabsorption and secretion. But those can be relatively simplified, because what do we know about reabsorption and secretion in the human body? What are we going to be talking about? I've asked you this a dozen times, so I hope it's sinking in. What is the physiology behind reabsorption and secretion? Help me help you. I got one person that answered. I got 16 people that are here right now. Yeah, protein transporters. So what you're going to have to do is go through and look at all of these different protein transporters. This is not as hard as it looks. Every single one of these protein transporters you've been exposed to this point. So just take a deep breath. And let's remind ourselves of what we're even dealing with. If we are moving something from the renal tubule back into the cells and then most likely back into the bloodstream, man, we're going to have active transporters Carrier transporters, these are going to be everything from facilitated diffusion to secondary active transporters that you've heard about, and then just open channels, so passive diffusion, right? Active, active, passive, completely passive. Is everybody with me on this? Some of this carrier stuff is facilitated diffusion, so it's passive too. So this just takes you right back to AMP1. Awesome, cool. So we got a list, we got a table for each one of these. Now, the last thing here is, man, if we're talking about primary active transporters, we're dealing with pumps. And what is the number one pump in the human body? It's found every single cell in the human body uses more ATP than anything else in the human body combined. Sodium, potassium, ATP pump. Awesome. Cool. Now, calcium pumps, that's what calcium ATPase is all about. This is your calcium pump, also one that we focused on in the past. And then hydrogen pumps. Hydrogen pumps have been, you know, they've been in pictures. We've never really described them in detail, but they're literally just an ATP pump that's moving hydrogen around. Not too hard to think about. If we need hydrogen to go from low to high, we use a pump. Does that make sense? Lovely. Now, carrier transporters, right? These are the symporters, the uniporters, the antiporters. These are porters. They're porting things across the cell membrane. What is a glucose uniporter? Well, uniporter means that it's only moving one thing. So what transporter have you guys learned about that's only moving glucose? What are the abbreviations for this glucose transporter? Perfect. Not SGLT, Ashley. Good try, though. SGLT, yep, you got it. You fixed it. Awesome. Because what else does SGLT transport other than glucose? You got it. Well, no. I mean, yes, but no. What's the S stand for? I love you guys. You're overthinkers. You're true students. It stands for sodium, right? So SGLT is a sodium glucose symporter, and that's the next one on the list. So sodium glucose symporter, which means that it's moving sodium and glucose. It's moving sodium down its concentration gradient to move glucose up its concentration gradient. This one's SGLT. Yes, no, maybe so? So we got our GLUT, we got our SGLT. We got a sodium bicarb symporter, and we saw this in the digestive system. We just didn't focus on it too much, but sodium bicarb looks a lot like the sodium glucose, looks a lot like the sodium amino acid symporter that we also learned in the digestive system. So again, it's moving sodium down its concentration gradient to move these other things back up their concentration gradients. Does that make sense? Sodium hydrogen antiporter, moving sodium down its concentration gradient to move hydrogens the opposite direction. Chloride bicarb. What am I dealing with here as a chloride bicarb antiporter? What did you guys learn the name of? Something that's moving chloride in one direction, bicarb in the opposite direction. What are we dealing with here? Good, Becca, good memory. This is chloride shift, and this is going to be pretty darn important in this unit coming up as we're talking about pH balance. So make sure you guys know about chloride shift. Last but not least, in the carrier porter system here is the sodium potassium 2-chloride symporter, which we've already seen is found in what part of the nephron? Where do we know we have lots of these sodium potassium 2-chloride symporters? What anatomical portion? Yeah, part of the countercurrent system, but what anatomical is the thick ascending limb of the loop of Henle? Cool? Everybody that just didn't want to type that down, did that make sense? We've already seen these. We already know where they're at. Okay, cool. Channels, sodium channels, potassium channels, and aquaporins. Aquaporins are just those water channels that I've mentioned a few times. Now, channels, easy peasy, passive diffusion or osmosis, right? That's just allowing things to freely move. In the thin portion, Melissa, it's all water in the thin portion of the loop of Henle, but we're talking about the thick portion. Right, this thick ascending limb of the loop of Henle, lots of salt symporters. Sodium 2-chloride, potassium symporters here. Only the thin portion's water. Cool. Sometimes that's what it takes, is what we did in class, that drawing that we did personally, that's the trigger for the memory. Okay, so what you guys are going to need to do is you're going to need to walk through a number of things, a number of what we want to reabsorb. Sodium, glucose, water. Urea, I won't test you guys on. Bicarbs, hydrogens. These are the primary ones that I will test you guys on. Urea I'll put at the very end down here because I don't want you guys focusing too much on that. It's easy. Urea is easy. It's passive reabsorption. About 50% of all urea gets reabsorbed. So, yeah, whatever. The other ones, boom, sodium through hydrogen. I gave you guys a list of what you should be studying. Sodium, glucose, water, bicarb, and hydrogens. What do you guys need to know about these? You guys need to know which transporters are found where in the nephron in order to move sodium, glucose, water, bicarb, and hydrogens. Okay? That's what I will focus your test questions on. What do I mean by that? For instance, glucose reabsorption. Glucose reabsorption, look at this little diagram way up here. Where in the nephron does it occur? Only in the PCT. 100% of glucose reabsorption occurs in the PCT. 100%. So what do we know about glucose transporters? Do we find them in the descending or ascending limbs of the loop of Henle? Do we find them in the DCT? Are there any glucose transporters in the collecting duct or the collecting tubules? No, 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 right? Where we have structure, we have function. So the only way that 100% of glucose can be reabsorbed in the PCT is if 100% of glucose transporters are found in the PCT. Does that make sense? How? You've already learned this. Okay, this is part of the digestive system. Glucose, we're not talking about galactose. We're not talking about fructose. We're talking about glucose. That's what you're going to be tested on. So if I'm moving glucose from the tubes, from the tube of the PCT, this is the lumen right down here, then this is the apical surface. If I'm moving glucose, glucose is relatively low in that PCT compared to the cell. So if I'm going to move glucose from low to high, what transporter do we know will allow glucose to move from low to high? It uses sodium concentrations for its function. Now we're talking about SGLT. Good, awesome. And as the glucose is moved from low to high, now it's causing even a higher concentration of glucose inside of this cell. This cell, these tubular cells, don't really use a lot of that glucose. They want to move that glucose back into the bloodstream. So it's going to move it from high to relative low. So what transporter would we have in place on the basal surface for this function? Good. This is GLUT. And this is GLUT2, by the way. So this is GLUT2. This is just like that universal GLUT that can move any monosaccharide around. Okay? Exactly. It don't care. Not too hard, right? Good news is we have lots of sodium out in the lumen of the tube because so much sodium is getting filtered. It's small, it's got a positive charge, so it can go right through that negatively charged basement membrane. So lots of sodium gets filtered. So we got a high concentration of sodium out here. So now we're reabsorbing sodium. We're going to have to do something with that sodium. I'll teach that to you in just a second. And we're getting lots of glucose back out of this PCT. Where does 100% of glucose reabsorption occur, everybody? Good. PCT only. PCT only. So what do we know about these transporters? Any transporters, carrier transporters are rate limited. They can only move so fast. I think students often forget this, is that these are these carrier transporters that are open. They're like C-shaped. They're open on one side. So on one side, they bind what they need to bind. So those two things must be in the system. Then they close, they open, they go through a conformational change, and they release on the other side of the cell membrane. Then they close, then they open, close, open, close, open. This is a rate limiting step. It can only go so fast. Does that make sense? This isn't, it can't go light speed ahead. It can only go so fast. Now it goes fast. It's like the speed of a turbine, but it's still limited. And the PCT only has so many SGLT. It only has so many. There is a maximum number that this PCT can have. What I'm trying to get at is, what if we saturate the PCT with glucose? We hypersaturate it. What's going to happen to the amount of glucose that's getting reabsorbed? Well, if we've hypersaturated all of the glucose transporters, then not all of the glucose can get reabsorbed. Does that make sense? If we've hypersaturated every single one of these transporters, the SGLTs, they can only move so fast and there's only so many of them. So what if glucose does manage to get out here in the thick descending limb of the loop of Henle? What are we going to reabsorb it somewhere else? Where's it going to end up? Where does water want to be? This is diabetes, right? When the blood glucose levels are so high, glucose is going to get filtered. And it's just, small, positively charged, boom, goes right through the fenestrations and that basement membrane, and glucose goes into the PCT. In a normal patient, healthy patient, 100% of glucose is going to get reabsorbed there. But in a diabetic patient, they are filtering so much glucose that the transporters can't possibly keep up. And that extra glucose goes down into that descending limb of loop of Henle, and bye-bye. We can't reabsorb it at that point. It will end up in their pee. So one of the most obvious diagnostics of a diabetic patient is whether or not you find glucose in their urine. Does that make sense? That's all it has to do with these transporters. We're going to talk about it. It's called saturation. We're going to look at some curves and stuff for it. Sodium reabsorption. Now, sodium, you already saw this SGLT moving some sodium into the cell. We are going to need to get that sodium from the cell and into the blood. What do we know is already in place on the basal surface? It's moving sodium every microsecond of every day, uses more ATP than anything else in the human body. Every cell in the body has this thing moving sodium out of that cell. It's the sodium-potassium pump. Yes, no, maybe so? So on the basal surface, we have a sodium-potassium pump. Awesome. This is going to help regulate everything from resting membrane potentials of all these cells. It's also going to be moving any extra sodium that builds up inside of this cell for whatever reason. It's going to move it back out towards the blood. We have it on the basal surface, not on the apical surface, because we don't want to move sodium back out into the lumen. So where we find the transporters is important. So sodium reabsorption in the PCT, we're talking about SGLT, sodium reabsorption, and the rest of it is just passive. We just got a sodium channel. We just insert a whole bunch of sodium channels in the apical surface. If we have a high concentration of sodium out here, and sodium's always getting pumped out of the cell, so we have a low concentration of sodium inside the cell, then sodium's just going to passively diffuse back into these cells. Does that make sense? Don't worry about the rest of everything going on right now. Does that part make sense? There's a lot more to this slide, but focus on one thing at a time. 65% of all sodium reabsorption occurs in this manner, just by passive diffusion and via SGLT symport. 65% of all the sodium reabsorption occurs in the PCT. It's a number you guys should write down. It's an idea you guys should write down. That means the large majority of sodium transporters are found in the PCT. 25% of sodium reabsorption occurs in the nephron loop. Where in the nephron loop could possibly be reabsorbing sodium, along with a couple of chlorides and a potassium? Yeah, thank you, Ruju, for answering. I go wait here all day for everybody else. This is that sodium to chloride potassium symporter. It's going to be a big part of your exam. It's going to be a big part of your lab practical, and it's going to be a big part of a case study that we're going to work on. So make sure you guys are following the emphasis as I try to say, write this down. And I say it over and over and over again. The redundancies for a reason. In this thick ascending loop of Henle right over here, we have those sodium 2-chloride potassium symporters. And they're absorbing 25% of the salt. That doesn't account for 100% of the salt reabsorption. 65 plus 25, we're only dealing with about 90. So what's going on with the last 10%? Good. I like your thought process. P, sure. Kind of. It could all potentially go out in the urine. But do we want to be peeing out 10% of our salt all the time? And DCT and CT and CD, those are good answers too. But do we always want to reabsorb that extra 10% of salt? Probably not either. So don't we want a way to fine-tune or regulate how much salt is excreted and how much salt is retained? We want a decision in this, don't we? So what are we going to use? What do we know about the DCT, the collecting tubule, and the collecting duct? These guys are dependent upon what for their function? Hormones. So when we're talking about sodium reabsorption, is there a particular hormone that jumps out at you? Aldosterone. Good. So what's happening out here in with sodium regulation and DCT collecting tubules and collecting ducts? Well, now we're talking about principal cells. You guys remember how I made the joke about P cells because they help you pee? Ha ha ha. I do it on purpose, right? It just creates a memory. It doesn't have to be a good joke or anything. But this is going to finalize the concentration of your pee, both water concentration and salt concentration. These P cells have lots of receptors on them or in them. And one of the receptors that we find in the P cells is the aldosterone receptor. Why is the aldosterone receptor inside of the P cell? How does that work? How can we have a receptor for a hormone inside of the cell? A cytosolic receptor. What do we know about ONS? What do we know about aldosterone? Is it polar or nonpolar? It's actually not about the flow of sodium, Heather. Good try, though. I like that. What do we know about ON? All hormones that end in ONE, testosterone, progesterone, aldosterone, cortisone. Good job, Becca. These are all steroid-based. Is that ringing a bell from Unit 1? I know it's a long time ago. Aldosterones are steroids, so they're non-polar. Therefore, can they just move through the cell membrane? You better believe it. So where are we going to find the receptors for steroid-based hormones? In the cytosol. Yes, no, maybe so? And what do we know about cytosolic receptors? This is going to really test your memory from Unit 1. All steroid-based hormones, they're not fast, they're slow. Good try. That was a memory. That was a part of your memory, Melissa. It's the opposite. Where polar molecules are fast, non-polar molecules work slowly because of what Heather just wrote. Good, Heather. Great part of that memory. Does that ring a bell for anybody else? I'm not just going to tell you typically. I like to make you guys use your own rememories. Yes, I said rememories. Deal with it. Cytosolic receptors interact with DNA. Yes, no, maybe so? This is going to cause a change in DNA activation. And DNA is all about being a template for protein production. We got a recipe for making proteins. Yes, no, maybe so? Lovely. Cool. Now we're on board. So these P cells start making new proteins when aldosterone's in the system. Again, I love that Melissa brought it up. Is this going to be fast or is this going to be slow? Yeah, this is going to be slow. It's going to be pretty darn slow here. Okay, that's going to come back and be important a little bit later. So what do we need in order to reabsorb more sodium? Well, we probably need more sodium leak channels, don't we? Because what's allowing sodium to be reabsorbed? Just passive diffusion of sodium. So we're just moving sodium into the cell. The more sodium leak channels, the faster sodium can be reabsorbed. Sweet. So aldosterone causes new sodium leak channels to be made. We're making more sodium leak channels. They're going to be inserted into the apical surface, and more sodium can now move into this cell. What else do we need? What's constantly moving sodium into the bloodstream? Uses more ATP than anything else in the human body. It's found in every single cell in the human body, moving sodium out of the cell all the time, every microsecond of every day, faster than a turbine engine. Sodium potassium pump. So we have more sodium to move. We should have more sodium potassium pumps. True story? So let's make some more. Aldosterone stimulates DNA to make more sodium potassium pumps. They insert them into that basal surface. Now, we can't forget about the last thing. It's easy to forget about. It's not even in this picture. Or maybe it is. I guess it is. There it is. Sodium potassium pumps. You cannot forget about potassium. You cannot forget about potassium. You got to take account of potassium. This is one of the few scenarios in the human body that potassium leak channels aren't found on the basal surface. It's not moving potassium back out into the blood. This is the body's only way, besides sweating, of getting rid of extra potassium. They are. How are we going to get rid of extra potassium? Where do we need to have potassium leak channels? On the basal surface or on the apical surface to get rid of it? We need it on the apical surface. So this sodium potassium pump, it's moving faster. We have more of these sodium potassium pumps moving sodium out of the cell and potassium into the cell. But now let's take that potassium that's rising inside of the cell and let's move it to where it needs to go. And in this particular scenario, P cells are pretty much the only way to get rid of potassium. So we put that potassium leak channel on the apical surface, and as we reabsorb more sodium, what's going to be happening to blood potassium levels? Increase, decrease, no change. Whew. Okay, so we got aldosterone. We've already written this down a few times, but now you guys see how it works. You could write your own flow chart for how this works. We got aldosterone that's doing two things: increasing sodium retention, reabsorption, but it's taking potassium from the blood and putting that into the filtrate. So that sure sounds a lot like potassium secretion to me. Does that sound like secretion to y'all? Okay, we got a patient with chronic low blood pressure. Okay, let's decrease that blood pressure. It's gonna be chronic for whatever reason, whether you have polyuria, diabetes, there's 1,000 ways that we can drop blood pressure in a patient. So we're decreasing MAP permanently. What hormone is going to be secreted the second MAP drops? Heart failure. Let's go ahead and say heart failure. So we got a decrease in cardiac output. I got a heart failure patient. That MAP starts to drop. Geez, my knees. Now we got renin. And renin, blah, 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 blah. And 2, ADH, and boom. So now we got a patient with chronic heart failure, chronic low blood pressure, chronic renin secretion, chronic aldosterone secretion. What's going to happen to sodium retention in those patients? Increase, decrease, no change. Good, Andy, great. What about potassium secretion? Increase, decrease, no change. So what's going to happen to the amount of potassium in the blood of those patients? This is called hypokalemia. And hypokalemia is a big deal because it starts shifting all of the resting membrane potentials of your neurons in your brain, of all of the electrically stimulated cells of the body, simply because we had heart failure. Let's go another one. Let's take and block. Oh, this is a tricky one. It's hard. But let's block sodium reabsorption in the thick ascending loop of Henle. So we're going to block sodium reabsorption here. That's 25% of sodium reabsorption. Let's go ahead and be as dramatic. This is never going to really happen, like that degree of sodium reabsorption blocking. We're just not going to do that. But let's block some sodium reabsorption here. What's going to happen to the amount of sodium that stays inside of the tube? Increase, decrease, no change. Good, 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 good. Sodium staying inside this tube because we block those sodium 2 chloride potassium symporters. Now, sodium's in this tube, and hormones can't keep up with it at first because we just blocked it. So where does water want to be? Party. So what's going to happen in the amount of sodium and the amount of water getting peed out? Increase, decrease, no change. So now we got polyuria. By the way, this is because we gave a patient a diuretic. This is exactly what one of the diuretics out there in the world does. It blocks sodium transport in that loop of Henle. It's called furosemide or Lasix. You guys ever heard of those? It's the same thing. It's a loop blocker, and it causes you to pee more. It's a diuretic. So now we got polyuria. So what just happened to urine volume? Increase, decrease, no change. I think we already did that, but what happened to urine volume? So what's going to happen to that patient's blood volume? Increase, decrease, no change. Oh. And as blood volume drops, what happens to mean arterial blood pressure? Oh. So what's going to happen to renin secretion and Ang2 and aldosterone and ADH? So what's going to happen to sodium reabsorption? Increase, decrease, no change. What's going to happen to potassium secretion? Increase, decrease, no change. So now we got another patient with hypokalemia. That's probably going to kill them if you don't catch it. You cannot give a patient a diuretic without giving them potassium supplements. You must do it at the same time. Otherwise, your patient will probably die or get really sick of hypokalemia, sue your hospital, sue your clinic. Somebody's going to lose a license somewhere. You're going to go in front of a board. Right? It's just basic, simple physiology. That's why we do this. Say that again. You might kill somebody if you're giving a diuretic. So this is why it's so dangerous for somebody just to take a diuretic. Anybody ever gone online and like weight loss programs without a potassium supplement, Melissa? Potassium, right? Because you're peeing all your potassium out. Why are you peeing out all your potassium? Because now we have constant aldosterone secretion. You've done them for shows. You've done diuretics. Oh, yeah. So you're actually competing for sure. A lot of competitive muscle builders, yeah. Or, physical, whatever. When you're trying to tone up or you want to get rid of all the extra water in your body, yep, they'll take diuretics, and it's extremely potentially dangerous if they do it long term. Yep. 1 day is fine. 3 days is not. So, cool. We're going to do some case studies on that, but I want you guys to, now, what about a diabetic patient? Diabetic patient, they're peeing out more glucose. Where does water want to be? Where are the parties at? You pee out more glucose, you pee out more water, urine volume goes up, blood volume goes down, blood pressure drops, renin is secreted. You guys starting to get the hang of this? Why do we call it mother effing renin? Because it's involved in so many disorders and can cause such bad downstream effects if we don't pay attention to what renin is doing. Water reabsorption. Water reabsorption's not too crazy. We got ourselves ADH, antidiuretic hormone, also known as vasopressin. This guy was secreted from the posterior pituitary, if you recall that from Unit 1. Therefore, it's secreted from a vesicle, therefore it's polar. And if it's polar, now it's got membrane-bound receptors. Ring a bell? So we have ADH receptors on those P cells as well. When ADH receptors are activated, they're going to alter the calcium concentration inside the cell. Why is calcium important? Because calcium triggers exocytosis. Yes, no, maybe so? Exocytosis of what? Exocytosis of aquaporins. The more ADH that's in the system, the more aquaporins will be inserted into the cell membranes, both the apical and basal surface. The more aquaporins are available, the more water can be transported. This is happening in the P cells. Everywhere else is what's called obligatory. So 65% obligatory water reabsorption in PCT, for instance. What do we know about the PCT? Is that it's reabsorbing about 65% of all the salts, 100% of glucose. So obligatory means it's obligated to move. Because where do we know water has to be? It doesn't just want to be there. It's like super peer pressure. It's got to be with that party. So if we're reabsorbing salts and glucose and all sorts of stuff here, water follows. The next idea has to do with water reabsorption in the nephron loop. And we've kind of already established this a little bit. It has to do with that counter current component. About 10% of water reabsorption occurs in the nephron loop. Now, I want you guys to take that same thought process and go back to, where is urinary, man, my eyeballs, here we go. I don't recommend getting old, y'all. Why do my eyes not work well anymore? Oh. All right. Here we go. So, you've seen this. I haven't really pointed it out in a lot of detail yet. It's been on models, so don't forget you guys' extra credit for urinary system anatomy that's due tonight at midnight. You've seen this on models, but you haven't been, tested on it. It's not part of the lab objectives or anything. And I will not test you on this, but it does help you understand the role of the thin loop of Henle a little bit better. The role is pretty simple. It reabsorbs water. But guess what? Humans actually have two different types of nephrons. All animals have two different types of nephrons. There's not just one nephron out there. Talk about starting to get more complicated, right? There's something called a cortical nephron, and there's something called a juxtamedullary nephron. Again, don't write this down. Don't overthink this. Cortical nephrons, look, they're mostly tubules. So cortical nephrons are all about reabsorbing salts. Their loops of Henle are very short. They do not dive down very deep into the pyramid. Juxtamedullary nephrons. These guys are all about reabsorbing water because they have a very, very long, thin portion of the loop of Henle. Yes, no, maybe so? So even though on that other slide I said about 10% of water reabsorption occurs in the nephron loop, that's in a cortical nephron. In a juxtamedullary nephron, that number goes way up. Which of these two types do you think humans have more of? Cortical nephrons or juxtamedullary nephrons? This is, yeah, go ahead and do your answers. Cortical or juxta? Let me put it into perspective. Oh, good, we got lots of people doing this. Cortical. This is the type of nephron that's found in animals that don't care about water. Now, of course, we care about water, but humans have evolved in areas that always have water. Even if you're living in a desert, you're living near an oasis, 1,000 years ago. It's not like you could just live in the desert and live off of everything. Does that make sense? Humans have evolved with easy access to water. No matter where you're at, there's got to be water. But what if you're an animal who evolved in the desert with almost no access to water whatsoever? Are you going to want to pee out any of that water? No, not a camel, Tariq. We'll come back to camels in just a second. Are you going to want to pee out all that extra water? Nope. Nope. You're going to want to reabsorb all that extra water. So in an animal that grew up in the desert, evolved in the desert, what are you going to have more of? Cortical nephrons or juxtamedullary nephrons? I love this. Gila monsters. Gila monsters are lizards, so most lizards are actually mostly juxtamedullary lizards and birds and stuff like that because they end up, you know, not having very wet waste. This would be a great example of, oh God, I love this little critter. There's quite a few little critters, but one of my favorites is the kangaroo rat. We have them here in Texas. They're real cute. Oh, kangaroo rat. They are so adorable. These guys are like 100% juxtamedullary. They're actually insect eaters. They're anything. They're like, you know, they don't really care. But the kangaroo rat, no, there it is. First question, why kangaroo rat does not drink water? They don't need water because they get all of the water that they need in the food they eat, in crickets and bugs and stuff like that. Oh, do they? I didn't know that. They're so, yeah, why not? I guess, right? People eat guinea pig. Why not? People eat cow. I guess whatever. Kangaroo rat works too. Now, yeah, I hope that makes sense. There's other animals out there like, I don't know, a mountain beaver. By the way, a mountain beaver is not a beaver. It's a weird thing. Why do they call it a mountain beaver? It's not a beaver. It's actually part of the, you know, Rodentia family, so it's a rodent. These guys here, not quite as cute. They live their entire life, pretty much their entire life, in or around a water source in heavily rainforest areas like did you guys all watch Twilight once upon a time? Most people have watched Twilight. So that was filmed up in Forks, Washington, which is actually not far from where I went to high school. And this is a massive rainforest. So if you look at images of Forks, it's just like a huge rainforest. They get over 200 inches of rain a year. It's just massive in terms of the trees and the amount of rain. Well, this is where we find animals that have easy access to water 100% of their life. Make sense? Not by choice. I agree, Tariq. Thrift books, why, oh, why are deserts dry? All about deserts. Cool. That's awesome. Thank you. Anywho, that's what we're getting back to here is this idea of water reabsorption in the nephron loop. I like to test you guys on it. I think it's important to understand this nephron loop and that it's all about osmosis. It's all about the length of the loop. We start changing the length of the loop. We start changing the amount of water that can be reabsorbed there. Everything else over here is going to be regulated by hormones. What hormone affects water reabsorption? That's ADH. Regulated, facultative. What does this mean here? It means that just because we have more aquaporins doesn't mean that water is going to get reabsorbed. What do we know water movement is dependent upon? No, not aquaporins. Just because we have aquaporins doesn't mean water's going to move. Where does water want to be? So don't forget that party, okay? Aquaporins is going to allow for more water to move only if there's party in different places. Yes, no, maybe so? The more aquaporins there are, now we can get a greater degree of movement of water. Awesome. What if we have an ADH inhibitor? What if we had an ADH inhibitor? What if we blocked ADH function? Good. Why? Because if we inhibit ADH function, there's less aquaporins in our cell membrane. So what's going to happen to the amount of water reabsorption? Assuming there's a party for it to go to. Increase, decrease, no change. and therefore more water stays in the filtrate and we pee more out. Can somebody give me an example? I know we talked about this earlier in the semester, but now is a good time to review this. What's an example of an ADH inhibitor? Just think of some things that make you pee more. Perfect. Not coffee, but caffeine. And yes, exactly. Alcohol is another one. Those are both ADH inhibitors. Does that make sense to everybody? Sweet. Potassium reabsorption is another one you guys need to know about. Most potassium gets reabsorbed in the PCT. 60 to 80% of potassium gets reabsorbed here. 10 to 20% of potassium gets reabsorbed in the nephron loop because of those sodium 2-chloride potassium symporters. Now, the rest is regulated over here in the DCT, collecting tubule and collecting duct. But we don't want to just talk about the P cells here. We also want to talk about the intercalated cells here. And we're going to look at potassium in conjunction with hydrogens and bicarbs. And we're going to be talking about these intercalated cells in more detail. So I'm going to go ahead and do it now. The way that I like to teach about these intercalated cells is just by using a table. There are two types of intercalated cells. There's type A and there's type B. On this image, you see type A. Type A intercalated cells. What are they always doing to potassium? As long as type A are active, what do you guys see? R, reabsorption, or S, secretion? What's happening to potassium? Reabsorption. So what the hell is a type B intercalated cell? These are very unique cells. Do you guys remember me teaching you about chloride shift? And how in chloride shift, the transporter flips. Intercalated cells are flipping at a much bigger level. The entire cell flips. Everything that was on the apical surface moves to the basal surface. Everything that was on the basal surface moves to the apical surface. So if I have transporters that are reabsorbing potassium in type A intercalated cells, that means those transporters are going to be found on the basal surface to allow for potassium reabsorption. But now in type B, it's flipped. So those same transporters are now found on the apical surface. So what's going to be happening to potassium in a type B intercalated cell if that cell is flipped? Reabsorption or secretion? Good. Awesome job. Does that make sense? So what we're going to do is we're going to write a table to help us understand this a little bit better and help us retain it a little bit better. We're going to write our intercalated cells, type A and type B. And then we're going to start having a couple of column headers. The first column header is going to be for potassium. We're going to ask ourselves again, type A, what are they doing to potassium? Reabsorbing or secreting? Type A are always reabsorbing potassium. Type B, therefore, are doing what? Secretion. Intercalated cells, we're going to see this in another slide. Intercalated cells, on the other hand, are acting, not on the other hand, in addition to potassium, are also acting on hydrogens and bicarbs. Are hydrogens acids or bases? Are bicarbs acids or bases? Type A, acid. Type B, base. If the body has too many acids, what's the body going to try to do about it? The body has too many acids. Are we going to want to secrete them, or are you going to want to reabsorb more so you die faster? Type A is always secreting acids. Oh, wrong color. Type A is always secreting acids. If the body has too many acids, type A, acid, comes into play to secrete them. What's it going to be doing in terms of reabsorbing in type B then, since it's flipped? Type A are constantly secreting hydrogen. Now what's going to happen? If we flip that cell over, what's going to happen to hydrogens? We're going to reabsorb them. Bicarbs are a base. So what if the body has too many bases? What are we going to want to do to all of those bases? Secrete or reabsorb more? Definitely not reabsorb. We want to get rid of them. We don't want too many bases is bad, right? So yeah, type B, base, we're going to secrete those bases. Now, if it's flipped, if I have a type A cell, well, here's the good news. Opposite. Remember what we just talked about. If the body has too many acids, what do we want to do? We want to get rid of them, but doesn't it also stand to reason that we're going to want to reabsorb more bicarb to buffer against those acids? Sweet. We got a dual process here. Type A cells constantly secreting hydrogens, reabsorbing those bicarbs to try to buffer against those acids. Type B, if the body is too basic, we want to get rid of bases and get acids back into the system. So we reabsorb those. Intercalated cells, primarily found in the collecting duct, but also in the DCT and the collecting tubules. They're driving this process. Don't worry as much about PTH and calcium and phosphate. You guys can look through this on your own. It might be in a homework problem, but I won't put this in the exam. Got enough to worry about. Hormones that influence sodium reabsorption. I want to remind you guys that it's not just aldosterone. That would make life way too easy. For instance, thyroid hormone. We saw that one of the major functions of thyroid hormone in Unit 1, we talked about the fact that thyroid hormone upregulates the number of sodium potassium ATP pumps. So if I have more thyroid hormone in my system, I have more sodium potassium ATP pumps, that is going to influence sodium reabsorption in the kidneys. Does that make sense? Growth hormone, Unit 1, we talked about the fact that it upregulates sodium potassium ATP pumps. We haven't talked about that with estrogen, but that's what it does. Cortisol, same thing. Insulin, same thing. All of these are going to be increasing the number of sodium potassium ATP pumps in the cell. Versus the opposite, AMP, progesterone, parathyroid hormone, glucagon. This is a slide you don't need to memorize by any means. The one I will focus you on is aldosterone. But I'm always trying to remind you that there's a lot more to the body than I can teach you. I'm sure that's already well understood by everybody, but I still want to emphasize that point. Okay? Okay. Tmax. We'll talk about this a little bit more in just a second. Let me see. We'll talk a little bit more about this in just a second. We'll come back to that. Reabsorption in the peritubular capillaries we'll come back to as well. Secretion. Remember that what we've been talking about when we've been talking about these intercalated cells is secretion. So we've been tying this lesson together. The primary thing that I will test you on for secretion, I highlighted and put in red for you. Secretion is always an active process. So it's always using ATP for its function. Always. Whether it's potassium, hydrogens, bicarbs getting moved around, always, always, always active. And the primary way that we go about dealing with both type A and type B intercalated cells, bicarb reabsorption, hydrogen reabsorption, y'all, this is the same thing we've been learning through Unit 3. What is the primary source of acid in the human body? Are you guys there? Did I lose you? What's the primary source of acid, hydrogens in the human body? Yeah, what molecule? There we go. There we go. Carbonic acid, which comes from CO2. Got it. Does that all make sense to everybody? And what enzyme converts CO2 plus water into carbonic acid? What enzyme is responsible for that? You could just use the abbreviation if you want. Carbonic anhydrase. Great. So in all the cells of the body that have more carbonic anhydrase, we're going to have a greater degree of this metabolic reaction where CO2 gets converted into water. In addition, anywhere that there might be more Ca in our fluid, this is going to occur, like our CSF, which we learned about for the respiratory reflex. So check it out. All chemical reactions are run on their gradients. So if I have lots and lots of bicarb and very little CO2, the chemical reaction goes back. Ha, awesome. Thanks, Tariq. Right, so bicarb, if I have a lot of bicarb and a lot of hydrogens, that is going to be combined in the presence of carbonic anhydrase into carbonic acid. We're going to be reversing this process, and that's going to dissociate in water to carbon dioxide and water. Well, carbon dioxide's small, nonpolar, shoots right into this cell. And the cell has high levels of carbonic anhydrase as well. So now it's just going to convert that back in the presence of water into carbonic acid, which dissociates inside the cell. This is the fastest and easiest way to get that bicarb from here to here. We're not transporting the bicarb across the apical surface. We're actually doing a quick chemical reaction, allowing carbon dioxide to fuse into that cell, and then the reverse chemical reaction to make the bicarb. I can't remember exactly what the number is, but it's something like 20 pounds of bicarbonate is reabsorbed every day. It's an insane amount of bicarb that is going through this process. It's a bucket of bicarb. Those hydrogens now just get secreted back out in the lumen. So the hydrogen concentrations out in the lumen stay high. Now, type A intercalated cells, what did you guys see? What are they always secreting? You look at your table in front of you. They're always secreting acid. Good, they're always secreting acid. So that's what we see over here. So in type A intercalated cells, we do the same thing. We're taking CO2, we're making the carbonic acid, but now our hydrogen pumps, just like over here, are found on the apical surface, and we got our chloride shift and our sodium bicarb symporters over here. Now, what's going to happen when we flip these? Type B intercalated cells. Now the hydrogen pumps will be on the basal surface, and the bicarb transporters will be on the apical surface. Easy peasy lemon squeezy? kind of. Not too complicated with your guys' background, I hope, crossing my fingers and toes. All right. Last little bit is going to go right into today's actual lab material. Today's lab is not long. Yeah. Relative. You got it, Tariq. I hope you guys never feel like I'm trying to make you feel dumb. That is definitely not my, that's not my purpose. Dude, physiology is hard. I had to study it for years and years before I started really seeing the connections. So yeah, I'm so proud of what you guys do. All right, excretion. Excretion is what's left over at the end of the road. Now, we can start to look at the composition of material that's in a patient's urine. Anybody ever peed in a cup? I think the answer is probably everybody. Right? And if we were doing today's lab in lab, I don't know what's going on here. That's not right. 1,000. It's actually 100 plus. But yeah, several times for pregnancy and stuff like that. Yeah. Anywho, if we were doing this in lab, you would actually be peeing in a cup. All right. And we'd be looking at some of the materials that are found in the urine. I'll give you guys literally probably the shortest introduction to your guys' lab today. And I'm going to have a PowerPoint you guys can work through to understand the rest of your lab. But one of the hardest parts of today's lab is that there is math associated with it. Okay, no clarification needed. As of right now, we're still on schedule. So if you look at your schedule, it's still all there. July 22nd, right? This is when all those exams are really going to start up. So we got another, week and a couple of days here. Cool. Anyways, what we want to look at is something called clearance. Clearance is used clinically all the time to monitor for renal function. Renal function is about GFR, right? So if your GFR starts to drop, we know renal function isn't working quite as well as it should. Did you guys catch that from lecture earlier today? And the way we can go about looking at a patient's excretion, not just the volume that they're peeing, but actually what's going into their system and what's coming out through the kidneys, is a process called clearance. And this clearance is going to allow us to have a very wonderfully non-invasive way to measure that patient's GFR. If we know how much is going into the system, and we know how much is leaving the system, and we have an idea of what should be happening in those kidneys, then we can get an estimation on how well those kidneys are functioning. What do I mean by this? Inulin is actually, it's a fructose fiber. It's a really cool fiber that was first found, I don't know, a couple hundred years ago, and then was started to use even as early as 1940s to start to look at kidney function, as bizarre as that might sound. A long time ago. Inulin is not naturally found in your body. And if it's not naturally found in your body, you're not going to have any transporters for it. Okay, there's no natural inulin substance, there's no receptors, there's no transporters for inulin. But it's really small and extremely polar because it's basically just a form of fructose that your body can't use. Anybody ever heard of adding inulin to your diet as a dietary supplement? I'm not sure how I feel about that yet. I haven't done enough research on it, but that people do that because it's a, you can't actually use it for energy. So it's basically just like a filler. It's a fiber filler. You know, it'll hurt your gut because the bacteria love it. Bacteria in your large intestines can eat this inulin like nobody's business, and it causes fermentation and gas, just like if you were lactose intolerant. Therefore, if you put in inulin, and you'll actually have to infuse this into your patient's blood, you have a known amount of inulin that you're giving that patient. All of that inulin is going to get filtered, and we do not have transporters for it. So how much of that inulin is going to be excreted? 100%, 10%, 0%? I know the answer is here, but does that make sense to everybody? Becca, you got it right off the bat there. Does that make sense? Yeah. So what if 100% is not cleared? What if 90% is cleared? Exactly. Now we know that there's possible kidney malfunction. So that is a measure, it's an indirect measure of how well that kidney is filtering. Does that make sense? Inulin is a pain in the ass. You know, doing these infusion tests and stuff on subjects, you're not going to be doing a lot of inulin tests out there in the real world. This is more for like lab and then real like research oriented studies. In real hospitals and even in veterinary offices and stuff, what they use is creatinine instead. And creatinine is something you make normal. Okay, so what you do is you take the patient's blood, you measure how much creatinine's in the blood, in the plasma to be more specific, and then you measure how much creatinine's in the urine. And based on how much creatinine is being excreted versus how much is in the blood, we can get a slightly less accurate, but accurate enough measurement of GFR. The reason why it's slightly less accurate is because we do have transporters that allow for the secretion of creatinine. So creatinine is both filtered and secreted. So you can end up with more creatinine in your urine in terms of concentration of creatinine in your urine than the concentration of creatinine that's in the blood. Does that make sense? Creatinine is not a protein. Sorry, I didn't read that. Creatinine is just a metabolic byproduct. It's just a chemical byproduct of muscle use. It's a breakdown from creatinine phosphate. Okay, cool. This is going to come back to haunt you in lab, so please, I hope you paid attention here. Yeah, I don't know. I guess basically it does have a nitrogen backbone, so it technically would be a I don't know. I'll have to look up a little bit more of that. How about that, Heather? Because I'm not an expert on the actual creatinine structure. I know it's a carbon ring with some nitrogens in it, but I think it's, I don't know. I don't know whether it has a hydroxyl end and an amino end. I don't know. Okay, now this slide here, and one more slide, and then we're going to talk about the urinalysis lab, and then I'm going to hopefully be able to let you guys go. This slide here is a reminder of the importance of urine volume. Urine volume is not of minor importance. It's of relatively major importance. It should be something that is in a lot of history. I've gone to doctors before and they don't ask me about urine volume, right? You go in and say you're sick and stuff like that, and they don't ask about, not the doctors, the nurses. It's not typically on their history checklist, but then the doctors almost always ask about it. And the reason why is because what do we know about urine volume and blood volume? Are they directly proportional or inversely proportional? So if that patient's peeing more, if they have polyuria, what if they're waking up 10 times in the middle of the night to go pee? What if you got an 8-year-old boy that starts wetting his bed? And we're not talking about a nightmare wetting his bed. We're talking about massive amounts of urine. We better start testing for stuff. One, we have polyuria, so we know that patient's blood volume starting to drop. They're going to start feeling really poor. Brain's not getting enough blood. So factors that influence urine volume, we could either decrease that urine volume or increase that urine volume, but don't just think of urine volume. Make sure you're thinking of blood volume. If we're decreasing urine volume with ADH, what's happening to that patient's blood volume relative to what would normally be happening? Increase, decrease, no change. ADH, aldosterone, increasing blood volume, decreasing urine volume. AMP is the opposite effect, fluid intake, right? We stop drinking so much, we're not going to pee so much. Decrease in blood pressure, pretty big deal, because as that blood pressure drops, the hydrostatic pressure drops and GFR starts to drop. Lots of things can affect urine volume. You go run a marathon and see how many days you have hypo excretion. I mean, there's lots of days afterwards where your body's just trying to recover from all the sweating. Or violently vomiting, diarrhea, hemorrhage, all of these are going to decrease your blood volume. And as your blood volume drops, your blood pressure drops. And as your blood pressure drops, GFR is going to drop with it. So all of those will impact your urine volume, whereas the opposite might hold true with the increase, right? Increase in blood pressure, increase in fluid intake. Certain disorders like diabetes or diuretics that you're taking, that sort of stuff. Cool. The last slide, I know Melissa asked me a couple of times yesterday about micturition. Well, she didn't use that word, but that's okay. Micturition is when you pee, okay? Micturition reflex is the nervous system reflex. I just did that drive from South Padre Island yesterday. You know, you're driving 6 hours. You guys know what I'm talking about? Like after the first hour, you got to pee. What's up with that? Why? Every single time you go pee before you go, and then you got to go again like an hour later. It's just got to happen. My physiology professor called it the Ellensburg effect because Ellensburg was right smack dab in the middle of Washington. So literally it was that you get in the car to drive, and where are you going to stop for your rest stop? So, you know, you driving up to Dallas, you might not stop, or you might stop in Waco, but I don't know. Waco effect, San Antonio effect. Nothing rhymes for me here. But the idea is the same as every other baroreceptor related reflex. Humor effect, yeah, exactly. Is that we have a detrusor muscle, we have a big smooth muscle sac, that's the urinary bladder, and there are baroreceptors. And so in normal, when there's just urine, maybe 100 mils, which is what's shown here, 50, 150, right? Well, it just kind of depends on the person and the size of the urinary bladder too. Urine's just chilling in here. Not a lot of pressure being put on the walls, but as urine volume builds up, more and more pressure gets pushed along these walls. So in normal, the internal urethral sphincter is nice and contracted, the detrusor muscle is relaxed. Well, now the baroreceptors fire. We have a sensory neuron. This is just a unipolar sensory neuron. It's traveling all the way up to the micturition center. Guess where that's at? Medulla oblongata, along with every other vital function of the body. Medulla oblongata. That signal now is going to send a reflex whoop, right back down to the sacral region of the spinal cord and back out to the bladder through some major nerves, pelvic splanchnic nerve and the pudendal nerve. I never test you on the nerve names. Feel free to learn them. You could always look them up later. If there's damage to the splanchnic nerve, for instance, now we're going to be affecting detrusor muscle and internal urethral sphincter. So yeah, I mean, there's definitely lower nerve damage in some patients, especially, even patients that end up with lower back inflammation. Maybe they have sciatica. You can get inflammation that ends up causing issues with bladder control. Crazy. Does that make sense though? Now we get this reflex back out that's going to cause the detrusor muscle to contract. The internal urethral sphincter is going to relax. We got a reflex that goes back out to the external urethral sphincter that's going to contract it even tighter. And it's going to wait for a somatic nerve signal to relax and let you pee. Yes, no, maybe so? Same idea as defecation, just using that same information. Sweet. Awesome. Okay, so thank you guys for all of your amazing patience. We're going to take another break here, just because I know it's lunchtime and you guys need to probably go, especially when you start talking about pee. Melissa, you got to go to work. Okay, sounds good. Now, in terms of lecture material, there's only one thing we have left to go through for quote-unquote urinary system. However, it's not really urinary system stuff. I mean, it's a combination of the entire human body. It's the urinary acid-base balance. We will be doing this tomorrow in lecture. Come with your smartest brain possible. This is a culmination of everything that you've learned this semester. It won't be easy, but it will be easier if you remember that the body is comprehensive, that everything we're doing has related to the next system. We were supposed to have done repro anatomy at this point. We're just going to push it off to next week. And then labs for Unit 4. We're going to be doing urinalysis lab. So the urinalysis lab is basically a pee in a cup kind of lab. And again, I've talked about this in lecture just briefly, but almost everybody's peed in a cup. Why is peeing in a cup so prevalent in the medical field? Because it's easy to do. It's non-invasive, relatively. Some people might feel like it invades their privacy, but it's non-invasive. It doesn't make you like stick needles anybody. And last but not least, because the kidneys are filtering your blood, your urine, oh my gosh, it's so powerful. All of these properties of the blood and human body function are ending up in the urine, and we can detect those in the urine using what's called urinalysis. Everything from the color of your urine, the odor of your urine, yes, I know that's gross, the acidity of your urine, the specific gravity, I'll give you guys a brief rundown on what that means. Glucose, proteins, ketones, blood, hemoglobin, bilirubin, urobilinogen, nitrites, leukocytes. Each one of these is a powerful indicator of whether the body is healthy or not. For instance, do we want glucose in our urine? Yes or no? No. Do we want proteins in our urine? Yes or no? No. Do we want blood in our urine? No. If a little bit of blood's in there, we might end up, you guys are like, no. You'll actually be surprised. There's, you can get trace amounts of blood in your urine pretty easily, whether it's from a minor urinary tract infection, bladder infection, or just the female menstrual period. So you can't just assume that since there's blood in urine that patient's dying. We'll go through some of these other possibilities, nitrites, leukocytes, all that sort of stuff. Discuss possible causes for abnormal test results and these characteristics and components of urine. Awesome. Okay. That is all in this lab handout. Remember, this lab handout exists for a reason, for you guys to be able to study it and use it on your lab report. So just like always, I'm going to unlock these lab reports for you guys. You will have a lab report due on Monday of next week related to this. You have a physical form that you guys can work on as a group. Obviously, you're not going to get a urine analysis result, so you do not need to fill this table in. However, you guys paying attention, you must know all of these normal values. Is that clear? These normal values you will be tested on. They're not too bad. Glucose, absent. Bilirubin, absent. Ketones, absent. These are all normal. Blood, probably shouldn't have that. Proteins, probably shouldn't have that. Nitrites, leukocytes, these are all like immune system stuff, inflammation, right? Those should be absent. Making sense? Most of them are null, like you shouldn't find them in the urine. Other things we should find at some levels. When we start seeing glucose in the urine, boom, now we got an indicator of a disease, or bilirubin, or ketones, so forth, so on. Make sense? So that part of the lab really isn't that hard. Understanding a urinalysis, it's not that complicated. I promise you that. I put on a virtual lab PowerPoint. This is a really cool PowerPoint. It's going to walk you guys through this lab, so I'm not going to do that for you, not this go around. So this virtual lab's kind of fun. When you guys go to do it, come on, enable editing. What did I open it twice? What happened here? No, just open once. So what you're going to do is you must watch this as a slideshow. Okay, you can't just go through it like this. It won't work. This is an interactive PowerPoint. So put it in as a slideshow. You can either click this button down here, or you can go up to View, or I guess Slideshow, and then play it from the beginning. I'm just going to click Go. It's interactive. Oh, I wish you could hear it too. This is just fantastic. Don't worry, more's coming. Yep, that just happened. Oh yeah, and it's a very pronounced audio that goes with it too. So this is an interactive slideshow. I can't build something like this. I stole it from somebody else. I'm not gonna lie. And as you click your mouse, it speeds up processes, except for this very first one. And now you can see that there are instructions. Click here to start the lab. Boom, I'm clicking on it. What do I need to do? Okay, macroscopic observations, chemsticks urinalysis, microscopic you will not need to do. So you don't need to do the microscopic observations. Click here to continue. Urinalysis lab, at any point, you can use your escape key. If you're just starting this lab, you should click the continue button. Oh, okay. You see how easy this is going to be to walk through? It's really interactive. Click on the blackboard to view a larger blackboard for discussion. Boom. Tests on urine can provide clues. It's such a powerful method for a non-invasive diagnostic. At any point you can use, click here to continue. So now it's going to walk you through each one of those macroscopic observations that I told you you must know normal for. Color, turbidity, odor. Why do we care about color? Why do we care about turbidity? Turbidity has to do with whether or not there's particulate matter in there. Why do we care about odor? I know it's gross, right? No, normal odor for urine is a slightly nutty smell. Yes, as a nurse, you will be smelling urine. Sorry. Different diseases can cause different odors to the urine. All right, and then it's going to walk you through the different chem sticks, right? How do we use urinalysis sticks? What each one of those values actually means, what normal is, negative over here on the left is all normal. You're using a colorimetric assay, so as you dip your urinalysis strip down into the urine, it's going to cause that urinalysis strip to change color, just like a pH strip, right? It's going to change color based on how much glucose is in the system, how much bilirubin's in the system, ketones, specific gravity. That's one I will still explain to you because I think that's tough for students to learn on their own. Everybody on board with what you'll need to do? Love it. Thanks, guys. Awesome. So that's going on there. I want to spend a couple seconds on the lab report itself and on specific gravity. So specific gravity is it's an easy idea once it's explained. Specific gravity has to do with the density of a liquid. Please write that down. Specific gravity has to do with the density of a liquid relative to water. Specific gravity has to do with the density of a liquid relative to water. What does this mean? Salt water, is it more dense or less dense than pure water? It's got stuff in it, right? It's saturated water. So is it going to be heavier? Is it going to be lighter? This is a property of specific gravity. Since we're making everything relative to water, we set water to 1.0000. We literally are setting water to 1.0000. That's the specific gravity of water because water is the same weight as water. Does that make sense? We just set it to 1. And if something is more dense than water, then it has a value, a specific gravity value greater than 1. So if I have 1.001, yes, it doesn't seem like much of a difference to y'all, but that is 0.001 more dense than water. Yes, no, maybe so? Versus 1.030, that's 0.030 more dense than water. It's quite a bit more dense. You know, if you're dehydrated, that means your body has lost water, but you still have lots of salts. Well, now you're going to be peeing those salts out, so your urine becomes extremely concentrated. We've all seen this. We've all probably had this happen to us. For some days, the urine's just more concentrated than other days. Whether you just got done working out or maybe you drank a little bit too much coffee. And the urine just tends to be a little bit more concentrated. Well, in that particular case, this value might be up here at 1.030 or maybe even 1.035. Now, if you have long-term dehydration, you're going to be looking at 1.04 kind of stuff. Does that make sense? If it's way high, I know there's a problem. If I'm all the way down here at 1.001 and am chronically at 1.001, I'm basically peeing out water. I'm not peeing out any salts at this point. Potentially, if that's chronic, that's a problem. Does that make sense? It means our body's retaining too much salt. Cool. You guys rock. Everything else is pretty straightforward. And I'll let you guys go through that PowerPoint presentation to do that. So lab report. The lab report, let's skip the math real quick. Okay, the lab report is pretty straightforward. The pigment responsible for the yellow color of urine is blank. I got a whole bunch of true, false, fill in the blanks. So where do we find the answers to these? Not online, because I gave you guys the answers in the handout. So all of these urine characteristics, volume, color, odor, turbidity, pH, specific gravity, abnormal urinary constituents, right? So if you're going through this, what you're going to find, oops, let's go back here, is the key words. Pigment responsible for the yeller? I just said yeller, that's funny. For the yellow color. Everybody see that in the text? Bilirubin, yellow pigment formed during heme breakdown. Bilirubinuria means that you have too much bilirubin in your urine. It's going to create a yellow foam when that urine sample is shaken. Sweet, awesome. Problem is, if we have bilirubinuria, you might get hepatitis or cirrhosis as your diagnostics. So this gives you every answer. This handout gives you every answer that you need to be able to answer all of your fill in the blank and true falses. Is that clear to everybody? You don't need to go searching online. The answer's here. Stop wasting your time on the Google, on the Dr. Google. Questions about GFR? Y'all, if I ask you a question about GFR, what equation should you be writing down? Students overcomplicate this all the dang time. I try to teach you guys all through the semester how to use your equations to understand physiology. So what equation? That's a good start, Tariq. You're not wrong. That's more like if we're going to be talking about the nephron, let's make sure we write down filtration minus reabsorption plus that secretion back in again. But on this, I'm specifically asking about GFR. Exactly. GFR is now proportional to the net filtration pressure times that filtration coefficient. Did that make sense to the 12 people left over? And what do we know about net filtration pressure? Is there a formula that we can write down for that? I'm not going to make you guys do that. I know you guys know the answer is yes. So if I go over here to the lecture, I was doing this for you. Right, net filtration pressure is equal hydrostatic pressure in the glomerulus minus colloidal osmotic pressure in the glomerulus minus the hydrostatic pressure in that Bowman's capsule. Adds back in some colloidal osmotic pressure in that capsule. What value should this typically be? Colloidal osmotic pressure in that Bowman's capsule. So let me just take you back here. Which force that affects GFR is normally 0? This is the #1 missed problem on this lab report. It shouldn't be. Bowman's capsule osmotic pressure. So look at that formula. If I'm talking about osmotic pressure of the Bowman's capsule, osmotic pressure of the Bowman's capsule, that's this guy right here, osmotic pressure of the Bowman's capsule. Does this promote filtration or does it promote reabsorption? And we know that because it's got a plus sign. Favors filtration. You guys don't need to use 1,000 like horsepowers of whatever the heck I'm trying to say. You guys don't need to throw like all your energy into this. It's not that difficult. You just use your formula. Does that make sense? What is the effect of GFR if glomerular blood pressure increases? Okay. Which one of these values is glomerular blood pressure? Which one of these values, which one of these four is glomerular blood pressure? Blood pressure inside of that glomerulus. Does that make sense that that's going to be hydrostatic pressure inside that glomerulus? And I think that particular question says, yeah, it increases. So what's going to happen to GFR, y'all? If HPG increases, NFP increases, therefore GFR would increase, decrease, no change. So boom, you guys, I think, are now on board to be able to finish everything off. The last portion of this, what do we know about urine volume and blood volume? Directly proportional or inversely proportional? No problem. You guys will be able to answer those. Now back to the hard part of the lab. It's math. Eek. It'll be okay. It'll be okay. I'm here. I'm here to help. Even if you're working on this outside of class, right? You guys know you can text me. I hope you feel comfortable texting me with your questions. Calculate cardiac output, calculate renal fraction, calculate renal plasma flow, calculate filtration fraction. Dr. H, I hate you. What are you doing to me? Where do I even find this stuff? Cardiac output, you already know. How do we calculate cardiac output, y'all? And look at the two variables that I give you right off the bat. There's heart rate times stroke volume, cardiac output. How do we define cardiac output? If we were just to use words, let me do it for you. The volume of blood ejected from the heart over time. Yes, no, maybe so? So once I do this calculation, I'm going to end up with a volume, certain number, I don't know what 80 times 65 is. You guys can do that math for me real quick. That'd be great. You're going to end up with a volume of blood that's ejected over a 60-second period of time. 5,200. Awesome. So now we got 5,200 right here. Okay, this is 5,200 mils per minute because the beats are going to cross cancel. Schnicky, schnicky. That's the total amount of blood being ejected from the heart. So what am I going to do next? Something called renal fraction. Where do I find that? Well, it seems like Dr. H said that everything I need to know for this lab is in the lab handout. And there you go. There's an entire sheet of definitions and formulas. Renal fraction is the percent of cardiac output that goes to the kidneys. Huh. Okay. Percent of cardiac output. Don't we already have cardiac output? Didn't we calculate that? And now look at the other three things that I give you. I give you hematocrit, I give you blood flow to the kidneys, and I give you GFR. Which one of those is going to be important in renal fraction? If renal fraction is the amount of cardiac output that goes to the kidneys, the answers aren't in the handout. You still have to do the math. Everything you need, not the answers though, of course, because you still have to do those on your own. But yeah, so calculate renal fraction. This is blood flow to the kidneys relative to total blood flow out of the heart. So renal fraction is going to be what? 1040 divided by 5,200. Does that make sense? I'm just helping you guys. Renal plasma flow, amount of plasma that goes through the kidneys, amount of plasma that goes through the kidneys, amount of plasma. Dr. H started us up on this yesterday. And I was trying to teach you guys that if 40% of the blood is hematocrit, what percent of the blood is plasma? Yeah, Tariq, you got it, buddy. One sec, I'll come back to that. But yeah, 40% of the blood is hematocrit, then what percent is plasma? So this calculate renal plasma flow. Given the hematocrit, plasma is what percent? 60%. By the way, go back to what Tariq did. He mapped this out for us. 1040 divided by 5,200. It's 0.2. And if I take that from a fraction and turn it into a percentage, oh my gosh, 20% renal fraction. That's exactly what we want, right? 20% of your blood is going to your kidneys every minute. Yes, no, maybe so? What if less than 20% is going to your kidneys? Now we start having maybe a cardiac output issue. We start having heart failure. Filtration fraction. Now it's going to start getting a lot easier because filtration fraction just has a formula, GFR divided by renal plasma flow. We just did renal plasma flow, right? That's the plasma that's going through the kidneys, not total blood flow, but plasma flow. Well, plasma is 60% of 1040, right? And then we take and do our filtration fraction, which is going to be the GFR that I already gave you, divided by renal plasma flow. Cool. The next question is asking for clearance. Do you guys remember me saying that clearance is an indirect measure of GFR? It's kind of what I finished lecture off with, yeah? Clearance is an indirect measure of GFR, and we use clearance clinically all the time. We use inulin in a research situation. We'll often use creatinine as a kind of an easier method where we can just take a patient's blood and their urine and start to measure some creatinine. There's another one that we can use, which is called PAH. You guys don't need to know what that stands for. I hardly ever remember what the hell PAH stands for, but it's another one that they infuse into the bloodstream. And if you know that you're giving them 1.6 mg per deciliter, that's a known concentration in the bloodstream for what you gave them. And then we start to measure how much of that is cleared, how much of that is found in the urine. Then we can end up measuring that plasma clearance. Does that make sense in just terms of words? I hope, based on lecture and everything, I try to describe it a little bit better this semester. So mathematically, how do we determine plasma clearance? Plasma clearance is UX times V divided by PX. So what do these abbreviations mean? UX is the urine concentration of substance X. V is just volume, and PX is the plasma concentration of substance X. So that's your formula, UX times V divided by PX. Trick going on here. UX times V divided by PX. How many variables is in that formula? I know this is simple, but I want you guys thinking about how many variables. UX, V, PX. 1, 2. How many variables? It's only 3 variables. How many variables do I put in this question? Concentration of PAH in the plasma is 1.6 mg per deciliter. Its concentration in the urine is 2 mg per mil. At a GFR of 110 mils per minute, urine's being produced at a rate of 1 mil per minute. How many variables do I give you? So the trick is you need to find the 3 that are important. Okay? It's not a trick, that's real life. In real life, you're going to have a list of 400 things and you got to pull out just what you need. Does that make sense? Is everybody following? And I'm going to let you guys do that. I have faith in you. You can always contact me with questions for clarification. Everything else is a piece of cake in terms of I give you the formula and I give you everything you need for it. So for instance, filtered load, right? Filtered load is just GFR times the plasma concentration. The concentration of uric acid in the plasma is blank. GFR is blank. Easy peasy lemon squeezy, right? Just multiply those two together. Tubular maximum, 2 Tmax. Substance X, 66 mg per minute, GFR 110. What's the renal threshold? Well, renal threshold's just Tmax divided by GFR, and I give you Tmax, and I give you GFR. So again, just easy math, okay? Awesome. The lab practical, there will be math problems. On the lab practical, there will be math problems. You will have to do them, and you will use this definitions and formula sheet to help you with those answers. Is that clear? clear as acidic mud. Ouch. Awesome. That's it. That's your guys' lab. Please, please, please do that interactive PowerPoint. You'll be able to answer everything, have a much better understanding of what's going on with your analysis. It's a better explanation than I can give. All right, cool. Well, with that, I'm going to let you guys go. Please text me if you have questions. Please, please, please. I'm here to help. Office hours, y'all, get a hold of me and I'll meet up with you. I'm more than happy to at any given time. There's only a week and a half left, so you got to push hard. You don't score unless you score. Is yes, this lab report's due Monday, Andy. Yep. Don't forget, your renal anatomy's due tonight at midnight. Anyway, we can have longer. I've had students not be able to finish before because of the math. I will consider that, Ashley. I will consider it. No promises yet. All right, guys. Best of luck. Study hard. I'll see you tomorrow.